Okay, so so Umit is a good friend of mine from very very earlier years. So we met like almost 20 years ago, and he's now an associate professor at Carnegie Mellon University. And his research interests are in formal methods, programming languages, concurrency, parallelism, quantum computing, and AI and machine learning. He has numerous best paper awards. At POPL, QCE, and ICFB, and so on, and it goes. And he's very proliferate, so he has 2 books, and now he's going to tell us about bridging safety and performance.
Everybody, delighted to be here to talk about this work on bridging and safety and performance. As people are interested in declarative languages, I hope that you will appreciate the goal of this work is to bridge really good things about declarative languages and really good things about imperative languages, bring them together. So bringing safety and performance, really, as the title says. And this work has been going on for a while. The talk here covers about, let's see, 2016, so it's like about 8 years of work. A lot of people have contributed to this, probably dozens of papers, and some people have made major contributions, include my students, my research group at Carnegie Mellon, and other collaborators at other institutions, including Stanford and Northwestern. And so without their contributions, this work really wouldn't have been possible. So to put this work into some historical perspective, in computer science, as computer scientists, we somehow accepted this dichotomy between imperative languages and declarative languages. If you want to write fast code that, quote unquote, matters, we go and use imperative languages such as C, C++, maybe even Java. And the goal is to get good efficiency, good performance, because that's what matters. Now, if we want to play around with good ideas, we use declarative languages, functional languages, included in declarative languages. And our goal is really to write beautiful code, to have safe code. Safety is very important. But we know that we're going to get bad performance. Okay, and we accept that somehow. If we use imperative languages, we get performance. We do not get safety. If we use declarative languages, we get safety, but we do not get performance, and we are somehow happy with that. Well, I think this is unacceptable. And I think time is showing that it is unacceptable, right? Our systems are getting hacked. A lot of things are going very bad because of poor codes, unsafe codes. Yet, we continue, in some sense, living with this dichotomy. Okay, so why can't we just bridge this gap? Why can't we have both safety and performance at the same time? Well, I believe, of course, we can. And there are ways of doing this. I can think of 3 ways. One of them is improve the performance of declarative languages. Another way is to improve the safety of imperative languages. And the third way would be actually to include the capabilities of both so that we can express more and more things declaratively in some sense, and let the language handle a lot of the low-level tasks. So the second option here, improving safety of imperative languages, in some sense is already going on. There's a big effort in the development of Rust language. So I won't talk about that. What my interests are more about improving the performance of declarative languages and their capabilities. So points 1 and 3 is what this talk will be about. So from this perspective, we've been doing a ton of work in 3 different areas. One area is basically high-performance parallel functional programming, which may sound like an oxymoron, right? Parallel function programming is horrible in terms of performance. How can you make it have performance? I believe we can. I'll show you how. Responsive parallelism is taking parallelism, conventional parallelism, and actually enhancing it with better, much more interesting performance criteria. And the third angle is starting to actually manage very interesting performance properties within the language itself, within the runtime system, that I call automatic parallelism management. So in this talk, I'm going to talk about these two parts, the high-performance parallel functional programming and automatic parallelism management. Now, before I start, I think everyone pretty much knows, maybe I need not say this, but sequential hardware has gone into the dustbin of history. That's a fact. And almost everything today, ranging from your phones to our laptops to servers that are responding to your LLM queries, they are highly parallel. Parallelism is everything, everywhere, all at once, literally, right, in some sense. Yet, writing parallel codes remains to be challenging. Good performance requires extensive manual optimization, usually in imperative languages. Correctness is very hard because of concurrency bugs. So, natural question is, how can we bridge the gap? Well, it's not a novel idea that functional programming is safe for parallelism. Functional programming is beautiful. It's got clean and powerful syntax. If you add types, you get even more powerful things. It has a formal semantics. And it's parallel by default. You don't even have to think about parallelism when you're writing parallel functional programs because functional programming is parallel. You don't have to even think about it. It's just by default parallel. And it's completely safe, right? But performance is very proved hard to improve. There's been decades of work on this, right? Big effort in the Haskell community. It's proved hard. But it turns out it's doable. So this talk will show you how. But before we get there, let's develop some sense of how functional programming can allow you to write parallel codes in a very safe way. So here's the primitive. Okay, I don't want you to understand necessarily the code here. But this is a primitive that allocates an array and initializes it with a function specified by init. Okay, init is a this is a higher order function. It takes a function, it creates an array and initializes it. So this code does memory allocation. It allocates an array, and it actually updates these cells that it allocates, and it can do all of this in parallel. So it can do all of the array fills in parallel up to some log factor noise, so to say. So there's lots of parallelism here. Convincing yourself that this is parallel safe is not too hard. You just have to reason a little bit about the fact that you're not writing into the same location multiple times. But it's not too hard. And the par primitive there is the only primitive that you need for parallelism. So you only need a single primitive for parallelism, that's all. Okay? Now, once you have that primitive in your pocket, you can go ahead and write more and more complex things. You can map over an array of function, okay? And you can implement that by just these 4 lines of code. Okay, you just call tabulate, basically, that's it. Now, what's amazing about this code is that not only it's highly parallel, but it has absolutely no effects here. Okay, this is a purely functional code. Not a single effect. Now, not a single use of par either. Okay, it's parallel by default. Here is reduce. Okay, so it's a reduction. It's going by map and reduce. That's how you would write reduce in an ML-like language. Lots of parallelism. This is parallel safe. Absolutely no effects. Single primitive par suffices. So you can go on and write primitives like this over sequences. Okay, so it's really relatively easy. Once you have all that, you can start writing more interesting codes. You can do token counting by mapping and reducing. 3 lines of code. This is parallel. It's safe. Not a single mention of parallelism, but it's highly parallel. Now, you can say those are trivial things. How about more interesting things like graphs? Well, here's a parallel breadth first search. You can actually run this code. Okay? This is all that there is to parallel breadth first search. Now, because it's operating on graphs, it's exposing irregular amounts of parallelism. Note that not a single use of par exists here. Not a single effect exists here. Completely safe for parallelism. So, okay, so lesson is, well, using functional codes, you can write parallel programs, very interesting algorithms, not hard at all. Now, this is actually how we teach at Carnegie Mellon. We teach our undergrads parallel programming using this technique. In their second year, they learn algorithms, parallel algorithms and parallel programming at the same time in their main algorithms and data structures course. They excel at it, okay? It's that easy. Sophomores can do it. But when they run their code, they realize that things are not that easy because they actually end up getting very poor performance. They used to, I should say, which motivated all of this research. So now why? Well, it turns out fundamentally, parallel functional languages have come a long way. So you can improve compilation, you can improve optimization, but the main bottleneck, as pretty much is the case in any parallel thing that you want to do, is memory. There's already very high pressure on memory. Functional languages already exert a high pressure on memory. And when you throw parallelism in there, it gets incredibly worse, right? Because we have parallel tasks allocating at the same time. Now the memory manager must somehow satisfy that, as it also does parallel memory management, parallel garbage collection. Well, this is not a solved problem at all. It turns out parallel memory management, memory management allocation and garbage collection is very, very hard, and essentially an open problem. So this is in contrast to sequential memory management, which is, it's just like, again, very well understood problem, lots of algorithms, lots of different things you can do, but parallel memory management is not well understood at all. So why? Why is that the case? So let's dive a bit deep. So parallel computations have traditionally been modeled by using these DAG structures, where these nodes show or denote tasks that can be executed in parallel, and the edges denote dependencies. Now, you can take a program and map it to this kind of model, and theory people have developed many, many, many interesting algorithms, scheduling algorithms, analysis techniques, bounds, and so on and so forth using this model. Now, I should note that when I say theory, I mean analytical, what I call sometimes Turing theory, complexity theory-based approaches, algorithmic approaches. They have developed all kinds of interesting theories about how to reason about parallel computations. Now, being theoreticians, to them, memory is just another operation, okay? They don't necessarily account for the fact that memory is like 100x slower than your plus operation. And consequently, they largely ignored memory from this model. This fundamental model basically ignores memory, okay, for the most part. Now, in order to solve our problems, to establish this bridge, somehow we need to add memory to this model. How are we going to do that? So let's suppose that with each task, we associate the memory that it allocates. So in some sense, each task owns the memory that it allocates. And we draw these edges for use of allocated memory. For example, if task D uses a memory allocated by A, then we add this edge. So note that we don't distinguish between read and write. Just use is all that matters. Now, in 2020, we proved this theorem that basically said that if you have a deterministic race-free or declarative functional program, then this here has a particular structure. And what's that structure? The structure is that there are no cross edges. All of these edges go either up from a node to its ancestor or down from a node to its descendant. But they never cross. So you don't get these types of edges. You don't have edges between B and C, D and E, never. It turns out this is a result of determinacy, race freedom, or functional programming. Now, we call this property disentanglement. And you might say, whoa, that's such a strange thing. What is that exactly? Okay, why would you call that disentanglement? What's the essence of that? You might ask, like I asked. After some thinking, I realized there's something very fundamental going on here. What is that? What's that? So this DAG essentially is a generalization of a notion of time from a sequential to a parallel program. In a sequential program, everything executes sequentially, so the time is simply a chain. In a parallel program, things can happen simultaneously. So you need a DAG to effectively capture time. To actually represent time, you need a DAG. So disentanglement or this idea of no cross edges. What that's saying is that the use or dependency chains respect time. I only use a piece of memory that's allocated before me. That's it. Okay, so in some sense, it's a very, because it is a very natural thing, and somehow, I guess for a long time we missed it, but it came out as a result of this work. Now, perhaps given that understanding that this is just a generalization of the notion of time for parallel programs, it shouldn't come as a surprise that disentanglement turns out to be very natural and broadly applicable. So these are lots of benchmarks here. All of them are disentangled. Now, note that these are not all purely functional. They're not written all in a purely functional style. But even if they are not written in a purely functional style, if they're written in a purely functional style, they're disentangled. But even if you make various performance tricks and do not get out of the purely functional principle, you still remain disentangled. Okay, so all of these are highly optimized, really sophisticated algorithms, and some of them are really sophisticated algorithms, and they are all disentangled. Some of them include, in fact, atomic read-modify-write operations. They are still disentangled because atomic read-modify-write operations do not actually involve allocation because they operate on machine words or memory words. So it's very interesting. Now, okay, but what's the use for disentanglement? Is it just some intellectual exercise? No. Okay, so recall that our goal is to bridge performance and safety. And we need a tool to do that. We can't just continue doing, like what we've been doing because it proved hard. So we need a new concept. And disentanglement turns out to be this concept. And the idea is that disentanglement effectively says the independencies in computation tell you about the independencies in memory structure. If two computations are independent, D and C are independent because they're on parallel paths. There are no dependencies between them. That's what disentanglement says. It says that if there are independent tasks in a computation, they are actually independent in terms of the memory that they operate on as well. Okay, so that's the essence of what we get from disentanglement. Now, concretely, it turns out we can take disentanglement and turn it into an algorithmic idea to organize the memory into a hierarchy, independent, effectively, regions that mirror the computation DAG. So I'm going to show you how to do that. Suppose we have this computation and we want to execute it. What we're going to do is we're going to start execution at root and we allocate a heap, a region of memory. And when A forks B and C, we're going to allocate 2 new regions for them, and so on. Okay, we keep executing like this. Now when we join, okay, when we join, what we're going to do is we're going to unify all of those heaps on the left. I'm going to show that by simply merging into the parent. So they're effectively the same thing with a little bit of a squint. Okay, so with that squint, what we have here is what is a DAG here corresponds to a tree of heaps. Okay, so very simple structure. And the heaps, these 2 heaps are independent heaps because they belong to independent tasks in the computation. Okay, so on. So now, once you have this model, disentanglement tells you that all pointers in memory point up and down in this heap hierarchy. Okay, that's it. Basically, you have up and down and no cross pointers. Now, a nature of parallel computation is that when leaves are executing, all of the internal nodes are suspended. Okay, so that's an important invariant. And that's important because note that independent tasks can still communicate by accessing a joint heap. So they can still communicate by accessing a joint heap, but that's okay because that heap is effectively suspended. That's very important, it turns out. So based on these 2 observations, we can, as the computation execute, garbage collect heaps that are at the leaves completely independently with absolutely no communication with anybody else. Okay? So basically what the computation told you is that these are independent tasks, and what disentanglement tells you is that, well, because the tasks are independent, their memories are also independent. So you can garbage collect them at any point, whenever you want, with absolutely no synchronization with anybody else. Okay? Now, the internal nodes, it turns out, you can also garbage collect them because they're suspended. Okay, they're a little bit tricky because they have up pointers, so you have to be a little bit careful with roots. But that's okay. It's nothing unknown, okay? Memory management people have developed all sorts of techniques with dealing with things like that. And in terms of parallelism, that's trivial because it's suspended. So I can go and collect this with the memory. So it turns out this idea works really well in practice. And we have implemented it, and we saw some really good results. But one of the things that I'm very interested in is not just implementing things that run well in practice, but also understanding why do they do what they do. So consequently, okay, it works in practice, but does it actually work in theory? Okay, can we prove that this is efficient? Well, this turned out to be very difficult. After a few years of work, finally, one of my students actually got the brilliant idea that solved this theorem, Jatin Arora. And in POPL 2021, we proved that basically, that's a long theorem, I don't want to read that, but effectively, we can memory manage the memory of a disentangled parallel program efficiently. What I mean by efficiency here is very little overhead that we can amortize against the cost of the computation. And we haven't proved this, but it's not hard to prove that this is effectively optimal within a constant factor of the optimal. And the key idea behind the proof, which kind of, again, Jatin came up with, is a very novel idea. The idea is you don't just schedule tasks over your processors, which is what these languages do typically. You also schedule memory by scheduling these heaps. Okay. So yeah, so I highly recommend going reading over that paper if you're interested in this. It's some very good stuff there. Anyway, so it turns out that theorem, over the years, we've extended it from disentanglement to also entanglement, meaning that we can actually allow cross pointers, all sorts of interesting things. It turns out these are very rare, but you can allow it, and you can enhance the theory to account for entanglement as well. So you really, by following this approach, you do not lose anything. Now, the key idea for supporting entanglement is effectively to treat them as special pointers. The cost increases, but because they are so rare, in some sense that's okay. So implementing this took a fair bit of work, and we took the ML language, standard ML language, which doesn't have parallelism. We added parallelism to it with a single construct, the par construct, and otherwise we support the entire full language, including all FX module system. Everything is in there. And after years of work, we basically developed this compiler that we call Maple that's able to run parallel programs written in this language very, very efficiently. It uses both a task scheduler, as I mentioned, and also a heap scheduler to schedule the heap. Now, I'm going to show you some experimental results, okay, so how well this does, and then try to convince you that this bridging is actually entirely possible. Now, this plot here shows the speed up of our ML codes with respect to a C and C++ baseline of highly optimized codes. These C++ codes are optimized not by us, but by another group of people actually at MIT at Carnegie Mellon working together. They've been developing these algorithms over two decades now, I believe. And so very, very highly optimized algorithms, very sophisticated algorithms in there. And on 72 cores, Maple delivers 30x speed up over C++ sequential codes. And it's only 2x slower than C and C++, both in the parallel and the sequential case. Okay, so that's the lesson. So note that C++ codes are actually managing memory manually, so using highly optimized memory allocators. So this comparison is actually really apples and oranges. We're not comparing to a garbage collected language, we're comparing to a manually managed language, and the performance gap is factor 2. Now, really, we should be comparing to not C, but other memory managed languages. So let's do that. Compared to Java, compared to Go, okay, we are 2x faster. Okay, so that's important. C is 2x faster than us. This is normalized with respect to us. Go is 2x slower. Java is 2x slower. OCaml is 6x slower. Okay. I threw the OCaml in there just so that we have another functional language. Now you can say, doesn't that come at the cost of space? Because space is usually, okay, where functional languages pay. What's amazing is that we are actually better in using space than C codes. We are using 20% less space, okay? With respect to Go, we are using, I don't know, like 40% or something less. With respect to Java, we're using, or Java is using 4x more memory than us. OCaml is using about 2.5x more memory. So we are improving both in time and in space. We are improving even over the C code. Okay, so that's incredible. Now, summary of all that work. Okay, that's like, again, I said, 8 years of work there packaged into like a couple of slides. I believe high-performance functional programming is possible, and it's possible to bridge performance and safety. That's not, of course we need to be clever. Of course we need to do cool theory. Of course we need to do cool engineering, but it's possible. And also another thing I've learned over of this work is that it's always possible to improve your results, okay? All these results can be improved. I'm sure if we go back to the C people and say, oh, you know, we're 20% better than you, I'm sure they will be able to improve their results a little bit. And we might be able to improve it back. Really what matters is, in some sense, the methods. And the methods, what I've learned from this work is that you really need both the church theory and the Turing theory. By church theory, I mean formal methods and so on. Some of those theorems I mentioned required really significant formal methods effort to prove. And the Turing theory is really being able to reason about performance. That turns out to be really important because if you can't reason about performance, you can't design these algorithms that actually, runtime systems and algorithms that actually do well. So it's important to bridge not the two, safety and performance, and perhaps surprisingly, not surprisingly, to bridge safety and performance, you need to bridge the two theories of Church and Turing. And of course, experimental validation is very important. Any questions so far? I can take a little break here and handle your questions because the rest of the talk is somewhat independent.
The previous slide where you have the different languages, we looked at Clojure. No, I have not. Because it has very basic, small primitives that handle parallelism, but its concepts or its assumptions are very different than yours. Okay. So the idea in Clojure, as I understand it, is that it assumes local garbage is very fast to collect, so it maximizes local garbage.
In some sense, our allocator does that as well, so it kind of maximizes local garbage collection, yeah. That turns out to be very important, in fact, for efficiency reasons, yeah. But yeah, so we should compare to Clojure.
The kind of way you described it is you had the heaps, and then you allocated subheaps, and then you could just collect those subheaps. Does this kind of translate at all to something like a compacting collector where it's going to be moving things around because things are...
Yeah. In fact, that's a very good question. Yes, so here, it turns out these leaves are trivially compact. You can use whatever collector you want, actually. You can move, if you want, you can mark and sweep, but you can also move and compact. And the collectors that we use move and compact. That's very important because it's locality and so forth, yeah.
Think of these, this tree as like a conceptual thing, not necessarily how it's laid out in memory. Okay.
So I think I'm abstracting over stuff, a lot of stuff here. And yeah, so the implementation is very, very different from what I've described here. It obliges by it. It respects it, but it's very different. There are a lot of details, yeah. Good question, yeah.
It is very cool stuff, Umud. I have a question. If you go to I found those two lines, mumble speed up over C and then 2x slower than C a bit confusing. I'm assuming the slowdown is yes, the sequential. So that means the second bullet implies some parallelized version of C and C++, or am I?
Right, I went through this very fast. So that's a very good question, right? So these performance measurements, we have to be careful about them. So what we did here is, typically you compare a language to itself, because you say, okay, I speed up, this much time compared to my sequential version. What we did here is we compare Maple's parallel version to C sequential. So we're like really very hard on us in some sense, right? We done sequential C codes. Does that make it clear? Oh, so this one here, yeah. So this is the parallel version of our codes are 2x slower than parallel versions of C codes. Yes, yeah.
How does one parallelize the C code in this case? I'm just curious. What sort of library or what we use?
Oh, so this is work by Julian Schut at MIT and Guy Bilalak at CMU. They have been like developing basically a library-based parallel C codes. So they're most interested in implementation and algorithms. So they develop cool algorithms, implement, et cetera. Yeah. So we're comparing to their work. So that's not. Yes.
So thanks, great work. So I would like to know what is the speed up with respect to the number of processors. So because here you have 72 cores and do not use. So what happens? So if you because usually so I'm impressed by 72 cores that you can also have such speeds up, but because often you get this for a slow null number of cores, you get a good speed up and then it turns down.
Right, absolutely, you're right. I mean, so these speed ups are incredibly good. So obtaining speed ups on 72 cores is not a child's play, because really that's pretty much the max you can obtain because of the hardware constraints. Even if you have 72 cores, typically the max, because of the memory bottlenecks, the max you can obtain is 30 cores. So we're 50%, I think of it as. So max you can obtain is 36. We're getting to 30, very, very close to max possible.
The speed up of 8 if you have 8 cores. Good.
Papers and whatnot, we go to 72 cores, whatever, 144 cores and so on. Any more questions? Yeah.
Functional and imperative programming, you haven't mentioned the fact that many imperative algorithms rely heavily on destructive assignment on arrays. When you're parallelizing functional algorithms, it's usually a pain in the ass how to simulate that. Do you think this is relevant for this discussion? I think that you're using merge sort and not a quick sort or with update in place. Can you elaborate on this?
Not actually, yeah, of course. So I think that to repeat everybody. So in imperative languages, you typically use very different paradigms of programming than in functional languages. In functional languages, you're copying data all over the place because you're not allowed to update them so much. And in imperative languages, you typically update everything in place. So there's a huge difference between the kinds of codes that you write. Now, our codes, it turns out, because of the way that we've abstracted our codes, organized our codes, almost all side effects happen in what we call sequence libraries, array libraries. So the user codes do not typically do any side effects or anything like that, but everything is happening at the level of abstract data types. So we've been able to basically, by using functional programming paradigm, push all of the dirty tricks inside array libraries. So the programmer pretty much writes functional code. And that's how these codes are written, yeah.
Maybe continue with this. Many of the optimizations done in imperative languages rely on heavy use on cache memory and utilization of that things. How does different hierarchies of of memory levels?
Very good question. So this is a research direction. It's well known that, in fact, so I did some work back in 2000, 25 years ago, that showed that you can take these bags and schedule them to improve locality on hardware. We are not doing any of that here. But it turns out, research direction, that's possible, and it would probably be fruitful. But some of it, I should admit, happens naturally, it turns out, because of the way we schedule things and so on. So that is an important factor here.
And maybe also
Yeah.
handling the arrays, that's where the case thing improves.
So I think all of these could be fully automated, right? And we can, in fact, manage locality automatically as well. That's, again, a research direction. Yeah, so very good question. There's a lot to do here. And we can, there's perhaps another, I don't know, 50%, perhaps 2x improvement that we can get by doing things like that here. Yeah, very good question. Okay, so thank you all. I'd like to move on, and we can take more questions towards the end. So good. So in the second part of this talk, the question is, can we increase the reach of declarative programming so that the language does more of the really nasty optimizations that we have to do by hand automatically? Okay. So it's a reality that parallel programs require extensive optimization. And an unoptimized parallel program runs at least 10x slower than a sequential one, okay, by default, just like that. And the key optimization that you do is what's known as granularity control. And the idea is to not parallelize small pieces of computation. Very simple to say. But it turns out it's a huge headache, and huge headache to actually deal with this in practice. Let me just give you a simple example. So if you have a par4 primitive that iterates a number of loop iterations in parallel, you can write tabulate like this. This allocates an array and fills the array in parallel. Okay, very simple to write. If you run this code without optimization, you're going to get 100x slower. You're going to be 100x slower than an optimized piece of code. How does an optimized piece of code looks like? It looks like this. You first have to make parallelism explicit so that you can control its grain. The problem here is that it exposes too much parallelism. So if you talk to people, people sometimes say, oh, parallelism is hard. There's not enough of it. No. That's not true. The problem is parallelism is easy. There's usually too much parallelism. The problem is there's too much of it. So you have to spend a ton of time to manage it. That's why you get like this 100x slowdown. So you really need to do things like this where you say, okay, I'm going to explicitly expose parallelism, and I'm going to put a grain on it that says, if my problem size is small, then revert to a sequential piece of code. Okay, that's what this does. Now, look how ugly this is. But it's not only ugly, but it's actually almost impossible. Because what should this grain be? Should it be 10? Should it be 100? Should it be 1,000? Okay, what should it be? Well, there's really no good solution because it depends on what this init does. Init might be a tiny function, set this element to 0, or it might be go compute Fibonacci 20. It could be a giant function. So there is no way to determine that grain, period. Okay? So it's an unsolvable problem because it depends on dynamic dependencies and dynamic data. Now, worse, the init itself could be parallel. What if init is parallel? Then what do you do? What should the grain be? Well, nobody knows, okay? So what people do is they just throw random constants in there, hope for the best, okay? And what happens is you spend hours optimizing, and what you end up getting is a nasty piece of code that's overfit for your hardware. If you try it on a different hardware, of course it doesn't work because the constants are not optimized for that hardware, and so on and so forth. So there ought to be clearly a better way of doing this, but it's not easy. Okay, so how do we do this automatically? Somehow, what we want is write this code and use my daughter's favorite book to pick the right grain. Okay, so that everything works. How do we do that? So it turns out this is possible. I'm gonna try to explain the idea with a metaphor. Now we all need oxygen to live, right? And think of oxygen as parallelism. In a parallel computation, you have to supply parallelism constantly. That's your goal. And in our bodies, we have to supply oxygen to all of our cells. That's our goal. How does our body work? It has a heart. It beats, and it supplies oxygen not continuously, but discretely. Only at the heartbeats, it supplies the oxygen. Okay, so this was the inspiration. Can we do the same? Somehow, parallelism, like the oxygen, we're not going to try to expose it continuously as we traditionally do, but actually do it discretely. Okay, how are we going to do that? Okay, so the idea is what we call heartbeat scheduling. So you take your DAG and you execute sequentially. You're not even worried about the oxygen, okay? But you note the parts where you can create parallelism. You just kind of take a little note of the parts where you can create parallelism. And you have a heartbeat that's beating at every millisecond or so. And when the heart beats, you go and create parallelism, but only when the heart beats. In between the heartbeats, you're doing actual, honest-to-God sequential work. Okay, so that's the essence of the idea. Now, we proved in a PLDI 2018 paper that with some care, you can do this with no loss of efficiency and no loss of parallelism. Okay, so the no here is a little bit of quoted. The actual theorem is quite a bit complicated, but what no means is arbitrarily small. Effectively, it turns out, by speeding up your heart, you can supply as much parallelism as you want, and by slowing it down, you can supply less of it, and so on and so forth. But there's usually a sweet spot, obviously, system setting. Now, this proof is very tricky, very, very tricky. We didn't believe it ourselves because it turns out like this theorem, when you start thinking about it, it's actually very hard because the problem is that if you delay parallelism here, you're delaying all of the parallelism that parallel task is going to spawn. So in some sense, you expect impacts to accumulate. You do not expect to be able to control parallelism. You do not expect no overhead from this approach. Because if my heart doesn't beat here, I'm kind of screwed. Because my oxygens are going to start my cells are going to start suffocating. So my heart needs to beat up faster in order to catch up. But we're not using anything like that here. We have a fixed heartbeat. Okay? So it's actually a very tricky theorem. But it turns out it's possible to prove. And the key idea is that when you're parallelizing, you can't just parallelize every task. You have to parallelize the uppermost, the earliermost task, it turns out. So that delay, the heart, makes sure that the biggest chunk of work gets parallelized. So we proved this thing. And it turns out, even though the idea is very simple, practical realization is it's a nightmare. It's very, very challenging, okay? How do you implement this hard? Do you implement it in the hardware? Do you implement it in the software? It turns out there are all sorts of overheads. So years of effort. So we did it both in actually ML and C, it turns out. And it works incredibly well. So this is a speed-up chart for, again, running up to 80 cores here. And we're writing codes with absolutely no granularity. There's no granularity control here at all, nothing manual. The system is managing parallelism using the heartbeat idea. And these are the self-speedups, okay? Speedups with respect to my one-count version. So incredibly good scalability, okay? So how do we actually compare to hand-optimized codes? Here we're comparing to hand-optimized codes. 25% slower than manually tuned codes. I was blown away by this. So you have a graduate student. Typically, my graduate students spend 1 day of their week to write an algorithm, 2 weeks to optimize it. Okay, that's the kind of effort, at least an order of magnitude. None of that happens anymore. You write your code, the system automatically gets you within 25% of the manually tuned code. It's incredible. Okay, so now, can we beat the manual? It turns out we can. Why? So here, we are comparing, this is the C implementation, the other one was ML implementation. This is the C implementation. We've compared our C implementation to OpenMP codes. And we are 50% faster than OpenMP codes optimized by others by using automatic parallelism management. Okay. How could this be happening? So we looked into it. How could this be happening? How could we be faster than manually optimized codes? Well, what's happening is that these optimizations are so tricky. Human beings do not do all of them, okay? So what we noticed is that OpenMP codes do not actually optimize certain parts of their code because they think, oh, this is too tricky, I don't know how to reason about this, and so on and so forth. But our automatic system is able to extract all of that. Basically, our automatic system is able to extract parallelism from complex pieces of code automatically where human beings didn't dare to parallelize. That was the lesson. Okay, so conclusion. It's not only possible to bridge performance and safety by using high-level languages, declarative languages, we can even improve over human beings. I guess computer science has now gone into an area where we are starting to improve over human beings, and that's sort of aligned with that kind of trend. And how do we do that? I swear by these methods. So I love Turing theory. I love algorithms, complexity theory, graph, view of computation, analysis, and so on. And I also love church theory. I like the fact that you can actually formalize what you're talking about, mathematically reason about it. So, and this work combines both of these things. And also, I love building systems. I'm a bit of a hacker myself. So lots of engineering has gone into it. In this particular, I should say that in this particular work, a lot of the hacking was done by my students, not by myself. So perhaps the key lesson from this work is church theory and Turing theory together can bridge safety and performance. And we've only scratched the surface. Lots of interesting problems to work on and lots of improvements to do. Yep, so take your questions. Thank you for your attention.
Actually, I have a question for you. So far, all of the examples you mentioned use like the fork join model. Have you thought about extending this work to like different paradigms, like futures, for example? Yeah.
A POPL paper, don't know what year, I think it's POPL 2024, where we showed that this entanglement extends to futures. Yeah, that's a very, very good question. So all of this work is fork join parallelism. It turns out this entanglement theory extends to futures. We haven't implemented it. That was just a theory paper. Yep.
Hi. A lot of the speedups that you measured for the heartbeat parallelism seemed to be measured looking at throughput. How does it affect latency?
So all of these benchmarks are, that's a very good question. So all of these benchmarks are not latency sensitive. None of them are latency sensitive. Now in another work with my graduate student, Stefan Muller, we have developed a different way of scheduling these computations, both for throughput and for latency. I don't think we consider the heartbeat at all. Let me think, just try to jog my mind a little bit. Yeah, that's a very good question. So I think it would work because the heartbeats that we are using here are like small enough, typically under a millisecond, that it shouldn't be a problem. But really research question, yeah. Excellent research question, thank you. Yeah.
On one of your slides, you made a comment in passing. I'd like to ask you to elaborate on, if you would. You said that you need to move the parallelism up to the top of the graph. Yeah. And how, if you're using external libraries that you didn't write and they're using parallelism or not, is this advice about moving to the top of the graph actually usable in practice?
Yeah, 100%. So we are assuming there's some kind of primitive that says fork or parallelize here. So what the runtime system will do, typically in a situation like that, what our runtime system does is to keep this graph of tasks in the background. So you start executing A, and when you see an opportunity for parallelism, you mark it, but you don't realize it. you say, this is a parallelism opportunity. You go down, let's say that you see another par here, you mark that, you say, okay, here's a parallelism opportunity. Only when a heartbeat comes in, and then the system decides which one of these, if I'm here, I have two forks that are available to me. Which one of these should I do? It turns out it's very important to do the top one. Why? Because there could be a huge computation here. You don't want to delay that. If you're lower, deeper in the computation, there's less likely to be more interesting things down there. Whereas here, if you delay this, you're delaying this entire thing. If you delay this, you're just delaying that little thing. That's intuitively what's going on. That turns out to be very important. Without that, the theorem doesn't go through.
So my question, I'm not sure if my question relates to your talk today, but I'm interested in parallel functional program for GPUs. So I'm wondering to what extent your ideas presented today carries over to parallel programming for GPU.
Programming is very, very different, as you know, right? Well, good question. I would hope that they generalize, but I have no evidence that they would, honestly. Yeah. So I'm sorry. Yeah. But we are working. I guess it suffices to say one of my students and I are starting to work on GPUs and trying to basically realize these ideas in the GPU realm. We're hoping that it would work, yeah.
I apologize, it's a very vague and nebulous question, but I'll ask it nevertheless.
I love those questions.
Okay, so the one very high-level takeaway that I have from your talk, as a very much an outsider, is that if you really want to make really squeeze the juice out of parallelism, it has to happen in the runtime.
I would agree with that. Yes.
Okay, so far so you agree, right?
Yeah.
Now, okay, so let's just assume that on the one hand.
Yeah.
On the other hand, it sounds, and so, on the other hand, it sounds like if you do this stuff with C, and you have Guy Blalock and his buddies just really hand tweaking the C and doing really insanely cunning things there.
Yeah.
There, everything, it requires a lot of thought.
Yeah.
But everything, all the cleverness is being sort of statically encoded in the program syntax. The runtime itself is, I'm just saying, it's probably not doing a lot of sophistication. Is that an accurate statement?
That's accurate, 100%. Yeah.
Whereas in your situation, the program syntax is, the syntactic is like super simple, like sprinkle a little par here. And all the cleverness is going to happen in the dynamic world, right? And yet the C thing is actually sometimes better, right? Can you speculate on, do you think in the limit the dynamic thing is always going to be better than what you can encode in the program syntax? Or is it just that, well, if you were a genius, you could do it in the program syntax and you wouldn't need this insanely complicated runtime, but it's just really hard to figure out the exact incantations in the program syntax?
That's such a good question. So let me, where was this? Let me go back to this plot. I think this is very important too. So, Ranjit, as you know, C is, so a lot of this overhead, it turns out here, that's C, that's us, is due to just the fact that C code is assembly, right? Like, so as a human being, you can move register-based stuff around. You can reason about your memory allocation. You can reuse memory, right? So those types of things. Now, they are always going to be faster. I think there's no way to beat them. But they are always going to be unsafe. There's no way, in some sense, the faster they are, the more unsafe they are. And that's the problem, right? Because as you said, these guys have been spending their past 20 years writing these codes. Let's say that I'm a software engineer and I want to improve that piece of code. Oh my goodness, I would not even dare to change a single line of code because I'm probably going to introduce a bug. Right? So there must be some cost to safety. Like, if you want your car to be safe, you must have airbags. You can't say that I'm going to be, I'm going to be safe without airbags. You must pay a cost. And I think I believe we are at the fundamental, we are really close to the limit of that cost with these techniques. And why? These, comparison to these languages show that. I mean, this is an industry strength language, Go. Okay? This is a language that me and my graduate students developed in a research lab. We are 2x faster. Java, we are 2x faster. OCaml, we are 6x faster, while consuming less memory, at least 2x less memory. Right? So that shows you how effective these techniques could be. Yeah, I hope that I answered it. So I believe there's a cost to safety. It's not going to be free. And in some sense, these higher level languages show you, Go's and Java's and OCaml's show you that even industry strength languages are paying a huge amount of this cost, but we are able to improve upon that. Yeah. Thank you. Yeah.
Like this R primitive that you introduced is not technically free, right?
100%, it's not free. Yeah. Oh yeah, sure. Yeah, I don't know if I have, that's what this granularity control does basically, right? Yeah, I think this here. Oh, here are the overheads. Yeah. On average, geometric mean 10% over sequential code. Yeah. But without the granularity, without automatically granularity control, this can easily be 10x or 100x actually, depending on the code. Yeah. Okay, thank you. Yeah.
No? Okay. So this talk is by Zach, and Zach and Yulia got the Best Student Paper Award here. And Yulia is my academic sister. So Zach is, this makes Zach a member of my academic family. So this session is, basically by my friends and family. So this is so funny. Anyway, so this talk is on answer set programming, and Zach will tell us about the stable model based semantics for answer set programs containing conditional literals and arithmetic.
I don't think so. I don't know. Would you give me a hand with it? We'll see if, because that's like the login screen.
Yeah.
Not seeing anything.
Oh. I think this is.
All right. Of course, now I can't find it on my computer.
Okay, so you might notice this. Is your cursor lost?
Yes. All right, thank you. So Maybe I'll just leave it in this format for safety's sake. Yeah, so this is SM-based semantics for answer set programs containing conditional literals and arithmetic. And in particular, we're interested in defining semantics for answer set programs in a way that's convenient for formal verification purposes. And in particular, we want to be able to automate the verification of answer set programs. All right, so to begin with, we'll just consider basic answer set programming rules of the form head if series of body, b sub 1 through b sub n, where h is either an atom or it's empty, denoting it's a constraint. And each b sub I is singly, a doubly, or a non-negated atom. And alternatively, each b sub I could be a comparison between two terms, like x is less than 5. So this is a very traditional rule, but it has a very flat structure, which on the one hand is attractive from readability perspectives. On the other hand, it loses some of the expressivity that you might get with a first-order formula, where you can have arbitrary nesting of quantifiers and different connectives. So one kind of happy medium that at least the Klingo answer set solver employs is allowing these body literals to be replaced with conditional literals. So a conditional literal is a structure of the form h such that L sub 1 through L sub m, where h is a basic literal, a comparison, or the symbol denoting falsity, and the list L sub 1 through L sub m is a list of basic literals and comparisons. And this improves upon the expressivity of our rules. So this is a traditional encoding of the graph coloring problem in this language that we're talking about today. This is an example that doesn't use conditional literals, but I'll show how we can refactor it. So the first rule is just a choice for assigning color to every vertex. The double negation is basically the choice rule syntax, sugar stripped away. What I want to talk about is the third and fourth line, which is the constraint that every vertex must be colored. To achieve this, we have to introduce this auxiliary predicate colored, a verity 1, which is actually unnecessary, and it's problematic from a formal verification perspective because it extends our program signature. So if we want to talk about arguments of strong equivalence, for instance, this program is actually less than optimal because of this colored predicate. So what we can do is we can refactor this program and instead we can omit this colored a verity 1 definition and instead add this conditional literal that's the red expression. So we're saying for all vertices, it's impossible that it hasn't been assigned any color with this conditional literal. So to go forward, when we're talking about conditional literals, we have to talk about variables that are global to a rule versus variables that are local to a conditional literal. So in this example here, V is global because it occurs in the head, but not in the list of conditions within our conditional literals. It's also global because it occurs in the vertex V atom. All other variables, which in this case is only C, are considered local. So the intuition that we're going to formalize with these semantics is that conditional literals behave like nested implications within rule bodies, universally quantified over the local variables. And again, the motivation for this is automating the process of program verification and extending the class of programs for which we can apply this automated verification. So Anthem's a tool that I've been developing in collaboration with a number of other people at Potsdam and also Vladimir Lifshitz from UT Austin. It's a tool written in Rust, and it uses the theorem prover vampire as a backend. So the main types of claims that we can automate with the Anthem tool are checking the equivalence of two ASP programs, in particular those written in the input language of Klingo. And the other thing we can check is that an ASP actually adheres to a first order, an ASP program adheres to a first order specification. What this work is trying to do is taking steps towards extending Anthem with conditional literals. So to do that, we first have to define the semantics of an extended language in essentially first order logic. That's the eventual goal. All right. So as background, I should talk about the logic of here and there, or HT, because of its close relationship with ASP. And I won't review the exact semantics of it, but I will say that it's a non-classical logic and it's intermediate between intuitionistic and classical first-order logic. So we consider in this work a mini-sorted variant of HT, where we have two universes, the first that consists of all program terms, and the second is a subsort of that universe. It contains an integer-like type that we call numerals. So equilibrium logic is an entailment relation for HT, and the intuition is that it introduces a stability condition on HT models. And there's been a lot of work showing the relationship with equilibrium models and the stable model semantics in terms of redux and so forth. So I'll talk about strong equivalence, which is denoted with this equality S symbol a lot as well. Formulas are strongly equivalent if they're HT equivalent, and programs are strongly equivalent, or ASP programs are strongly equivalent, if they have the same answer sets when paired with any other ASP program. And the nice relationship between ASP and HT allows us to check strong equivalence by checking HT equivalence. All right, so the input language of Klingo is called abstract Gringo, or HD, and technically the semantics are defined in terms of a translation tau into infinitary propositional formulas. So as a very simple example, if we have the rule P of x if Q of x plus 1, then tau applied to pi is the theory that consists of tau applied to all the ground instances of the rules. So that's where we replace x with all the possible symbolic constants, for instance, and all the possible numerals. So one important restriction of tau is that it replaces these conditions on the legal values of terms. So a term like 1 plus 1 has just one value, it has the numeral 2, whereas 1 plus a doesn't have any values, for instance. So the translation tau basically takes a disjunction across atoms with respect to all the possible legal terms. So in the case of symbolic constants like a, there are no terms, so it's an empty disjunction. Whereas in the case of numerals, we have exactly one value. So we can simplify the tau transformation into basically this infinite series of conjunctions across numerals. So Q of 2 implies P of 1, Q of 3 implies P of 2, so forth. So because Klingo promises to compute the equilibrium models of tau pi, we would actually like to lift this characterization to a first order setting so that we can avoid this infinitary context, which the main motivation for that is we want to use automated theorem provers for formal verification purposes. There are two steps we need for this. The first is that we need to replace tau with some kind of translation to first order formulas. And traditionally, these translations have been called tau star. The second step is we need to reduce the task of HT reasoning to classical reasoning. All right, so Mini Gringo is a fragment of the abstract Gringo language, and it does support arithmetic, which is one of the complicated features of the language due to this values of terms condition. The idea is that the semantics are captured via translation tau star into the syntax of first order formulas. But again, these formulas are interpreted under the HT semantics. We'll need additional transformations if we want to interpret them classically. So, as a quick example, tau star of pi applied to this same rule is going to be a fairly complicated formula, but it's strongly equivalent to a much simpler formula, which reads, for all x, if there exists an integer I such that I is equal to x, and q holds for I plus 1, then we conclude p of x. So when I use I and j and so forth, these refer to integer variables. Otherwise, they refer to variables that range over all program terms. So our goal is to extend this mini Gringo language with its support for integer arithmetic to programs that contain conditional literals. So one thing we've been interested in addition to conditional literals, is an extension to programs with aggregates. So integer arithmetic, conditional literals, aggregates, we've studied them all kind of in separation from each other. And this work is our first step into trying to bridge them all. So that puts us at the red dot, the intersection between arithmetic and conditional literals. The eventual goal for my dissertation, at least, is to bring both conditional literals and aggregates into this translation for Mini Gringo. All right, so to accomplish this, here's kind of an overview of the approach. We've got a variety of different logical formalisms and different ways of connecting the semantics of ASP programs within them. So if we have a logic program P, we know that we can transform it via the tau transformation into infinitary propositional formulas interpreted under the HT semantics. And this is basically what captures the behavior of Klingo. On the other hand, we want to design translations into the world of mini-sorted HT formulas via variants of tau star, because what we can then do is apply transformations on top of that tau star transformation, such as the SM operator, which is what I'll talk about today. Basically, that takes us into the world of classical second-order formulas, and there are known relationships between the results applying SM to mini-sorted HT formulas and the corresponding infinitary propositional formulas that you can obtain via a process known as grounding. All right, so some important features of the tau star transformation. I won't talk about the entire transformation, but basically, if we have a formula val t of v, it denotes that v is a value of term t. So for example, if we have this compound term val of x plus 1 interval 5, that's Klingo notation, of v, we can view this as the first order formula. There exists integers I and j such that v equals I plus j and x equals I, and j is one of the values in the interval from 1 to 5. And I didn't expand that formula. So if we want to translate a basic literal within a rule body, we have to take into account the global variables. So basically, we have a body translation, tau b of z, which translates atomic formulas in a rule body into first-order formulas. So for example, the literal not p of the term 1 interval 5 is there exists some v such that v is a value in 1 to 5, and not p of v holds. Here, the negation symbol is the HT negation symbol, which corresponds to ASP's default negation, or negation as failure. Not classical negation. That's the important point. The translation that we add to this existing tau star transformation is treatment for conditional literals. So if we have a conditional literal with local variables bold x, we would translate it into the universal closure across these local variables x, where the translation of the body literals conjoined implies the translation of the head of the conditional literal. So that was the main idea, that conditional literals behave like nested implications. The real challenge then was establishing that this is actually what Klingo computes. So as a running example, we would translate our conditional literal from the graph coloring program as follows. This is more complicated than it needs to be because there isn't any integer arithmetic in this rule. So this conditional literal constraint is actually, its translation is strongly equivalent to a simpler rule, which states for all vertices v, if v is a vertex, and for all c, color c implies that v has not been assigned to c, then we have falsity. So again, that's just an intuition behind the translation of a constraint rule in ASP. So the SM operator is convenient because it allows us to specify intentional predicates, and these are basically the predicates in which we minimize our belief. This is, in a lot of ways, a more convenient representation than the equilibrium models representation. So if we have a mini-sorted first-order formula and we have a list of predicate constants, SMP of f denotes this second-order formula. F conjoined with there does not exist u U is a tuple of predicates whose extent is less than P, and F star of U holds. So here, F star of U, you can think of it as a transformation that's embedding the behavior of HT satisfaction within a classical second order formula. And the condition that it's not the case that U is strictly less than P behaves analogously to the stability condition of equilibrium models in that we minimize our belief in intentional predicates. So in ASP, typically one of the rules is we don't believe anything we don't have to believe. On the other hand, there are certain predicates where we don't minimize belief. So for instance, the comparisons like equality, we don't minimize our belief in that analogously to other ASP predicates. All right, so for many sorted first order sentences from a signature, we call the models of S and P of F the P-stable models of F. We consider only standard interpretations that give a traditional treatment to arithmetic operators, plus, minus, times, and absolute value. We also assume other conditions like a Herbrand interpretation of symbolic constants. So finally, this brings us to our proposed semantics, which states if pi is a program and p is a list of all predicate symbols other than the comparison symbols, then the atoms satisfied by a standard interpretation are answer sets of the original program when this interpretation is a p-stable model of tau star applied to pi. All right, so to prove this, we had to prove that this definition was equivalent to the definition of Klingo's behavior, which are called Gringo answer sets. Basically, they're equilibrium models of tau pi. To establish this, we use the strong equivalence of infinitary propositional formulas. So the main piece of this work was proposition 2, which establishes that for a closed conditional literal, which means that all global variables have been replaced by program terms, then for a standard interpretation and the standard partition P, the grounding of tau b of z applied to this conditional literal is strongly equivalent to tau applied to this conditional literal. And here the standard partition just means that we treat all predicates except for the comparison symbols as intentional. All right, so our proposition 4 extends this to show that basically tau star, after the grounding operation has been applied, is going to be strongly equivalent to tau of pi. From this we can conclude theorem 1, which establishes the correspondence between the infinitary equilibrium models of this syntactic object grounding applied to tau star of pi and the infinitary equilibrium models of tau of pi. And our main theorem basically establishes that, yes, our SM-based characterization of answer set semantics captures the behavior of Klingo. All right, so I do want to talk, because this has all been like purely theoretical, I want to talk about what I've been working on since this paper was sent here, which is actually implementing this within the Anthem tool, because that's the eventual goal for this. So here are some very simple examples that we've verified. For instance, this example here replaces a choice rule in the first line with a conditional literal in the second line. It's been verified by hand in the past by the developers of the tau transformation, but now we can actually automate the verification of the equivalence, the strong equivalence of these rules by invoking Anthem with the command here. On the other hand, if we were interested in checking that our alternative versions of the graph coloring program are externally equivalent, which is to say that they have the same output for a certain predicate when paired with the same set of input facts, we can verify this automatically by invoking Anthem with the external equivalence verification pipeline. Again, these aren't strongly equivalent programs, but they are externally equivalent, which is a different notion we've been developing. All right, so to wrap up, this paper extends the mini Gringo language with conditional literals. And then we define the semantics of the language by extending the tau star transformation and applying a mini sorted variant of the SM operator to it. And we've proven that the proposed semantics actually capture the behavior of Klingo via strong equivalence. One of the reasons we pursued this is because it's a roadmap for this more challenging next step, which is trying to integrate aggregates into this language, which will require some additional work. And that's the main focus of future work, is extending this tool with conditional literals and with aggregates. All right, thank you.
I can ask some questions. So the so you motivated this work for augmenting ASP with kind of verification capabilities, right? So towards formal methods, and strong equivalence is something that we want to be able to prove automatically by using these kind of tools. So do you have in mind some other, forms of verification that may be useful? Not necessarily about strong equivalence, but maybe some other properties of, for instance, ASP programs.
So maybe I'll go back to, because I kind of glossed over this external equivalence characterization. There's actually a couple of different things we can test using this idea. On the one hand, we can check that two ASP programs have this special type of uniform relativized equivalence. On the other hand, we can check that a specification partially specifies the behavior of an ASP program. So if we write a specification in first order logic, we can check two things. We can check that the ASP program has the properties in this specification, or we could check that the specification completely defines the behavior. So there's an equivalence, an external equivalence between these two. So a special case of this would be checking answer set equivalence between two programs. That would be a special case of external equivalence. Beyond that, there's one thing I'm interested in is extending strong equivalence to programs with input and output. A lot of times we'll use placeholders in ASP programs, and it would be interesting to have some notion that two programs are strongly equivalent under certain assumptions governing the assignment of the placeholders, for instance, like that they're interpreted as integers, for instance.
So you said that you want to extend this work to aggregates.
Mm-hmm.
So, along that direction, do you think that first order will be sufficient, or will you have to move to a higher order?
Yeah, that's a really good question, and I think it's something we're not quite clear on. So we've been working with aggregates, trying to go back. Yeah, here we go. So we've actually got a paper at AAAI, this upcoming AAAI, where we define the semantics of aggregates as intentional functions interpreted under the HT semantics. So we have a pretty good understanding of how they should behave within the world of equilibrium logic, for instance. And there are reductions to first order logic. In fact, I think I had it. Yeah, this gamma transformation, gamma applied to tau star of pi, is one way that we can transform these mini-sort HT formulas with intentional function constants into formulas interpreted under the first order semantics. The problem is we need to have a bunch of additional axiomatizations governing our standard interpretation for aggregates. So for instance, we need to express that we have a sort representing sets of tuples, for instance. So we need a tuple sort, we need a set sort. With integer arithmetic, we've been able to use Vampire's native partial axiomatization of like integer arithmetic to overcome this issue. but they don't have something like that built in for sets and sets of tuples. So that's an ongoing question of, you know, there are lots of partial axiomatizations of set theory within the thousands of problems for theorem provers library, which is where we're drawing some inspiration for this, but it's definitely a challenging question.
So in the paper, when you talk about giving interpretation to like non-ground interpretation answer set programs, that's referring to the tau star operator. Is that a correct understanding of how those pieces fit together?
ASP program into something that's syntactically first order logic but should be interpreted under HT. And then we can apply additional transformations like Clark's completion or the gamma transformation to obtain formulas that can be interpreted under classical first order logic.
So is it potentially meaningful to take that interpretation and sort of run it like, you know, as a feed that to a solver and thus get kind of an interpretation for non-ground answer set programming? Is that like this tau star operator seems really interesting in the way that you're like pushing the semantics of answer set programming?
So you could definitely use like Z3, I think, would be an example of something where you could give it the formulas obtained via completion and tau star, and it could compute basically the stable models of the original program, which I think is how a SAT works. So there has been some research into doing this.
This talk and the perspective into a lot of different pieces that you have put together here.
The city we are located in is called Oxford, just to confuse matters even more. But the name Miami actually has importance. There used to be a tribe, a Native American tribe. I mean, they still exist, the Miami. But what I meant to say is that they used to live in this area. So Indianapolis is here, Columbus here. We are over here, more or less. They used to live in that area, and they were relocated forcibly. They now live in Oklahoma, in a city called Miami as well. However, they are working a lot on revitalizing their language. So the field of language documentation and reclamation is exactly that, kind of gathering information about the language.
Thanks for the talk. Just given the nature, I wonder if given the nature of the problem, it could be used an extension of ASP with probabilities, so probabilistic ASP, because I guess that you don't have strict rules for every case, so you can consider different possibilities with different probabilities, so that you get different solutions, each one with an associated probability. My impression is that the downside is that then inference is less efficient, of course, but perhaps it's worth considering that.
Several things. Sorry, several things I didn't understand. You have a group of native speakers who can say yes or no, this is correct, and do they agree amongst themselves? Are there dialectual differences? Somebody from the west and east disagree about whether this should be, I don't know, you just drop the E or not drop the E?
So I actually had a couple questions. I wonder, is ILDA interested in developing something like VerbNet out of these databases? Okay. And then the other thing that I was going to ask is I know, like Kowalski's logical English gives people a way to write in structured natural language something that can be transformed in a procedural way into Prolog. But I don't know if anything like that exists for ASP, and I was wondering if maybe you did. Oh, I meant if you wanted to write something in English that got transformed into a ASP rule. I don't know if there's anything that exists for that.
I think there are some systems that transforms controlled natural languages into ASP. But then Chita Baral and his students have been working on translating kind of English description, like stories or puzzle descriptions or so on and so forth, into ASP as well. So
So I live in Oklahoma. We have over 39 tribes, right? So do you think your system is extendable or portable for extending to other Native American language?
Firstly, a brief introduction. The abstract argumentation framework proposed by doing is the core form for many applications in the field of argumentation. It considers the arguments and the attacks between them. Each internally consistent subset output by it is defined as an extension, and one type of extensions corresponds to one semantics. The framework and semantics constitute a complete argumentation system. Moreover, answer set programming, a declarative programming paradigm, is recognized as a powerful tool for knowledge representation and reasoning in argumentation framework. Based on the abstract argumentation framework, Carroll proposed the bipolar argumentation framework to include the support relations. Then the weighted bipolar argumentation framework is proposed, which considers the weights of arguments or relations. However, the various weighted bipolar argumentation frameworks and their variants proposed so far have some shortcomings. Some of them fail to comprehensively address additional information, and the others neglect to evaluate the acceptability of argument sets. However, in the practical context of case reasoning, it is customary to encounter a variety of elements, including deterministic evidence, uncertain testimonies, relations between them, as well as the associated credibility levels. This situation matches very well with the application scenario of weighted bipolar argumentation framework. The And the objective is to identify the complete and acceptable evidence chains through argumentation. This iteration matches well with the extension semantics, which is mainly used to evaluate the acceptability of argument sets. Therefore, we propose a new weighted bipolar argumentation framework and its preferred semantics based on the principles of extension semantics. Moreover, we design and implement a reasoning tool based on answer set programming, and our objective is to process the additional information comprehensively, assess the acceptability of argument sets, and perform reasoning in weighted bipolar argumentation framework autonomously. Here we reach the second part, background knowledge. We begin with a concise review of the Duan's argumentation framework. A Duan argumentation framework is a pure F, including A and R. A means a finite set of arguments, and R means a text between arguments. If there is AB belonging to R, we will say A attacks B. And if S attacks each B with BA belonging to R, we will say S defends B. The semantics of argumentation framework is defined as a function. For an argumentation framework, the set S is called a sigma extension of F. Several semantics have been proposed, such as grounded, complete, preferred. The preferred semantic can be regarded as the maximum set influence among the acceptable argument sets. The preferred semantics here is defined based on the admissible semantics. Then the bipolar argumentation framework is proposed to include the support relations. To achieve an equal treatment of the attacks and supports, we refer to the method proposed by POPL'25. POPL'25 employs labelings to clarify the definition, which has been demonstrated to be equivalent to the extension approach. Labeling is a function which assigns a label to each argument, indicating accepted and undecided respectively. Then the deductive semantics can be defined here. A labeling L is deductive if it satisfies all these rules. Then the set S, including all the argument sets which are labeled in, is deductive. Similar to the previous, we can define the preferred semantics based on the deductive semantics here. Then we reach the third part, the weighted bipolar argumentation framework we proposed in our study. A weighted bipolar argumentation framework is a tuple, which takes into the weights of arguments and relations. To illustrate the semantics, I will introduce the definitions of violate and penalty here. For an argument A, if A does not belong to S, we say A is violated in the S. For a relation AB, if AB results in S failing to satisfy the deductive semantics in FBAF, we say AB is violated corresponding to S. Then the penalty of S in F can be defined as the sum of the weights of the violated arguments and the relations. We aim to minimize the value of penalty, so the definition of minimum penalty deductive can be defined here. A set S is minimum penalty deductive if there is no T such that penalty T is less than penalty S. Similar to the previous, we can define the preferred semantics based on the minimum penalty deductive semantics here. Then we compare the preferred semantics in the three frameworks from two distinct perspectives here. To facilitate the comprehension, we employ an example. like this. It should be noted that elements that are not marked with numbers are considered to have a weight of 0. And alpha is used to represent the weight is positive infinite. On one hand, we weaken the weighted bipolar argumentation framework to argumentation framework and bipolar argumentation framework to evaluate the expressiveness. The preferred extensions in different frameworks are calculated as shown in the table. Intuitively, the preferred semantics in weighted bipolar argumentation framework considers more constraints, resulting in a more limited extension set. Then we can prove that when the minimum penalty in F is 0, the preferred extension set in F will be a subset of the preferred extension set in FBF. However, this theorem does not necessarily hold for the AF scenario. Even if there are no attacks, the impact of support will also be taken into account in weighted bipolar argumentation framework, but this means all arguments will be accepted in argumentation framework. The preferred semantics in weighted bipolar argumentation framework can handle additional information on top of expressing and processing original information, showing better expressiveness. On the other hand, we strengthen the argumentation framework and the bipolar argumentation framework to weighted bipolar argumentation framework to evaluate the universality. The preferred extensions in different frameworks are calculated again, as shown in the table 2. By comparing table 1 and table 2, it can be seen that the preferred extensions of the both frameworks remain unchanged. Similarly, we can prove that if the deductive preferred extensions of the bipolar argumentation framework exist, the preferred extension set of the weighted bipolar argumentation framework will be equal to the preferred extension set of the bipolar argumentation framework. This equation does not necessarily hold for the argumentation framework scenario. And the fundamental reason is that deductive semantics has adjusted to treat attacks and supports equally, which changes the measurement of the attacks to some extent. To sum up, the preferred semantics in weighted bipolar argumentation framework encompasses the preferred semantics in bipolar argumentation framework, showing a degree of universality. In conclusion, its improvement of preferred semantics in bipolar argumentation framework is smooth, while its improvement of preferred semantics in argumentation framework is alternative. Then we apply our weighted bipolar argumentation framework to analyze part of the Abertrona mode case. And the table summarizes the arguments, their source, and their relation from the case. Then we generate the appropriate weights to the arguments and the relations. We contend that the weight of arguments is mainly affected by its source, and the weight of relation depends mainly on the strength of the attack or support. Finally, we model the case as the corresponding weighted bipolar argumentation framework on the left. The result can be proved to be consistent with the conclusions in the original case. If we change the facts of the case, given the assumption that Sabrina and Sarah did not quarrel, the results will change accordingly. It is evident that the incorporation of additional information can exert a pivotal impact on the outcome of argumentation. And the weighted bipolar argumentation framework we propose here possesses the capability to accommodate this necessity and adjust the results accordingly. Here we comes the fourth part, implementation. To realize the automated reasoning in weighted bipolar argumentation framework, we implement a reasoning tool, ASP-WBRT. The implementation process can be divided into 4 steps, including representation, decomposition, transformation, solving, and search. Firstly, we design the representation of arguments and relations supported by ASP-WBRT like this. They denote respectively weighted arguments, weighted attacks, and weighted supports. ASP-WBRT aims to solving the preferred extensions in weighted bipolar argumentation framework, whose underlying semantics lies in deductive semantics. So we decompose the attack and support representations into. So we decompose the attack and support representations based on the deductive semantics. This rule represents the weight of the rule if argument A hurts, argument B does not hurt is W. The rest of the rules can be interpreted similarly. It should be noted that the decomposition rules are not directly expressible in ASP. So we need to transform the rules to a form supported by the ASP. Then the weak constraint is given here. Weak constraint is a special constraint rule in ASP, different from ordinary constraints in that the answer set cannot satisfy the weak constraints in the program. Here's its basic syntax. For an answer set X, the ASP solver will calculate the penalty of X at different levels according to the weak constraints violated by X, with a higher level penalty as small as possible to find the optimal answer sets. It is evident that the mechanism of weak constraints can be used to solve the minimum penalty deductive extensions. Here's already a method to convert a rule like this into the corresponding ASP program based on the weak constraints. The representations can be transformed into corresponding ASP programs through the previous steps, and the solving results will be minimum penalty deductive extensions. Based on this, we can search for the maximum set inclusions as the final results. Then we evaluate the efficiency of our reasoning tool. And here's the experimental environment configuration. Owing to the absence of standardized datasets in each experiment, we designed a fixed number of arguments and generate twice as many relations as arguments randomly. And the distribution between attacks and supports is determined at random. Here's the result. The result shows that the runtime is almost proportional to the total number of arguments and relations. The reasoning tool can find the results in seconds when the total number is on the scale of 100,000. And the tool can find the results in 1 minute when the scale is in the millions. But when the scale reaches higher, the reasoning tool needs a long time to solve the problem. It can be seen that ASP-WBRT can reach high solving efficiency under a certain problem scale. Here's the fifth part, concluding and future work. In concluding, we propose a new weighted bipolar argumentation framework, which enables a more diverse range of representations. And we propose the minimum penalty deductive preferred semantics. which considers attacks and supports equally and handles weights based on penalty. Finally, we implement the corresponding reasoning tool, which achieves the automated reasoning in weighted bipolar augmentation framework and has significant implications for practical research endeavors. There are still many areas that need to be improved. Firstly, there is no comprehensive study on the reasonable range and treatment on the weights between arguments and relations. So we will try to explore more appropriate ways to handle them. Secondly, the semantics proposed by us only makes smooth improvements on the deductive preferred semantics in bipolar argumentation framework. So we will try to apply refined adjustments in other semantic contexts. Thirdly, there is no standardized dataset, but several metro data
Hi, my question is regarding the weights. I guess, if I understood it well, that it's the user that decides the weights, right? So depending on the problem, you have to assign the weights. Is that true? I mean, it's not automatic. It's part of the model. Okay, so my question is, could be possible to learn these ways from a set of examples, for example, from some data set or something like that? I mean, because I think that deciding the value of these weights is critical, and I don't know if you have a particular methodology to assign the weights or to check that these are the right weights, or to help the user decide the right ways, or to infer them from data, something in this direction. Have you considered?
generate some weights objectively and based on some standards like their sources, their credibility, their level of truth, and so on. And on the other hand, we plan to use the large language model to generate some weights, so we can measure between them and find better ways.
Okay. Okay, thank you.
So that question actually brought something to my mind that's more from the qualitative research area, is called inter-rater reliability. So if you're looking to generate weights, one thing you can do is, from a sample of people, see what the common consensus on a weight would be. Potentially that's more reliable than an LLM or something.
I noticed that you are using Klingo for the implementation. So did you use any of the optimization functions provided by Klingo? Well, because you were trying to minimize the penalty or something, did you use any tools provided by Klingo, such as like optimization methods?
I think, yeah. Oh, I need a minute. I might have to contact the committee again. Oh, yeah, I'm so sorry. Yeah, you're fine. Okay, I'm just gonna move it somewhere else. The mic's fine, okay.
You need the microphone. Yeah. So do you want to hold this and then I'll do the. Okay. Hello, everyone. Our presentation is automated playing of survival video games with common sense reasoning, and I'm Bryant Hargreaves.
My name is Dan Nguyen, and Keegan is not here today, and our principal investigator is Gopal Gupta, and we are undergraduate from the University of Texas at Dallas. So a bit of introduction. So this project is trying to autonomously play a survival video game that feature randomly but predictable generated event using common sense reasoning. And the reason we want to do this is to demonstrate that SCAPs and functional programming are effective tools to automate decisions in making actions to take based on random event. And so how do we do it? First, we collect the data from the environment, we convert them into predicates, and then we just use common sense reasoning to find possible actions and execute them.
So a little context of our common sense reasoning is we're trying our best to simulate human reasoning and the choices humans would actually make. So we do that in 3 parts. So our first part being default rules with exceptions and preference. And so essentially when our first example is if you say you have a bird, right? Given no other knowledge about having a bird, you would assume that it could fly. But as we all know, penguins are birds, but they can't fly. So to do that, we have default rules that say that something will fly if it's a bird, but if it's not an abnormal bird. And then we can later specify those rules saying that we have a bird Tweety, so we assume that Tweety flies, but we have a bird Sam, and we specify that Sam is a penguin, and so Sam cannot fly. And our next part is global constraints. So we have rules where there's an impossible choice. So we can't physically both sit and stand at the same time. And so we can say that's globally false and rule out that world. And so that brings us to our next part, having multiple worlds. We can have a situation where we have two professors, Mary and John, who are both professors and teach the database class, but John will be teaching if Mary doesn't teach a class, and Mary will be teaching if John doesn't teach a class. So in this scenario, there are two worlds where John is teaching and Mary is not, and the other one where Mary is teaching and John is not.
And so a bit background of the game Don't Starve. So Don't Starve is a survival video game. This is a gift, I don't know what it's in playing, but it's a survival video game where players learn to survive in a harsh environment that are safe during the day and dangerous at night. And to survive, the player must carry out certain action that can affect their hunger, health, and sanity. And player can equip, store, and items to aid survival, like making torch during the night or making campfire during the night, cook some food to eat. And most items can be gathered, crafted, and dropped from entities. So we call it Agent Wilson. Wilson is the first playable character that of the Don't Starve. There are multiple versions of Don't Starve, but this one is on feature like 10 unique playable character. And yeah.
Okay, so a quick overview of our agent. We have two main processes. One is the game modification, which interprets world data and sends it over to the server, which will convert the data to knowledge, combine the knowledge with rules, and essentially come up with the best action. And then we send that back over to the game modification, which executes the action and plays the game. Uh-oh. It's taking a second to load. Yeah.
Okay. Just do next one.
Okay.
All right. Go next.
Same thing. I don't know. Maybe it's
just do right here.
yeah. What is that? Oh. Which one?
Yeah. Okay.
It doesn't look my image.
Just do this right now.
Okay, sorry. All right, so it doesn't like this picture, but it's a nice picture. Basically, the world is composed of multiple parts. There's a lot of different entities on the screen which we have to interpret and find out. And we want to take it from the perspective of our agent. Okay, we want to take it from the perspective of our agent so that it's only the same thing is viewed as a normal human. So we get parts like what part of the day it is, the day-night cycle. We have data about health, sanity, and hunger. We have the player's equipped items, the inventory, the entities on the screen. So that would be campfire, things on the ground, trees, pretty much everything in the game, and important information about each entity, like tags and characteristics. So a tree is choppable and flammable. Berry bushes are pickable and also flammable. A lot of things are flammable, so gotta be careful. So yeah, this is our JSON data. It's a little hard to read, but maybe we can do it now. Okay. Perfect. Okay. So yeah, we essentially break things up into to parts, and so we have inventory. It's been condensed, so it's a little bit easier to read. You've got the GUID, the global unique identifier, and then tags about it. So whether it's can be used as a fuel source or it's collectible. And then you have is in light, so if it's not in the darkness, which is an essential part of staying sane. Other parts like health, sanity, hunger, other equipped and entities on the screen, and time of day.
Yeah, so with all that JSON data, we have to convert them into a predicate part. So like SCAPs can understand it. So you can see that we have the entity data. We convert them into like just like a predicate, just one fact at a time. Inventory, equip items, agent status. You can see that sanity. We convert numbers into like words to make it easier for the rules when we try to do it. And the world characteristic. So time, is it day, night, or dusk, and how close it to the next cycle. So yeah, if you go back one more time real quick, so you can see there are some underlined fact that we're gonna use. So item on screen is a evergreen, is a type of tree, and that tree is, you know that tree is choppable, so you can use an axe to chop it. And currently, the agent is equipping an axe right now. And we know that right now it's occurring in a daytime. And so yeah, this is one of the example rules. So I think in earlier slide, we have like 22 rules and like 8 assumptions that we made. So this is one of the rules. So there's an action at chop tree, with if only it is choppable, and it is, we have axe equipped, and there are not a lot of logs on our inventory, and and the time is not night, so we can safely go around and test out. So yeah, this is the output of it. There should be more than one output, but like, and then we rank them. So like how we so in SCAPs, we just query all of the possible model, and it is like we order it in the SCAP program itself. So when we query them, the one that is above it will split out first. And yeah.
So once we get the best action back from the server, we then do a bit of actions. So these actions can include wandering around, exploring for other items, gathering resources, picking up twigs, berries, stuff from the ground, cooking, so cooking at a fire, cooking your meat and food, eating, staying not hungry, managing inventory, throwing out items that you don't need because there's a limited amount of space in your inventory, chopping trees, and crafting and building structures. So like workbenches, campfires, things that give you more access to more features of the game, which you get more data, more items as you progress. So yeah, next is our demo.
So this is our demo right here. Just give it 1 second. So every time you make a new world, everything is different. It is randomly generated. So each world is different. And you can see that we are computing them in the background right there. And the big chunk of text is like the world data that we got. Okay, let's just run it for a bit. So before we continue on, would you want to guess how does agent die? Any guess? Yep. Starving. Good one. Any other guess? Tree falls on it. Any other guess? Losing too much sanity, which is terrible. Okay. Any other guess? It can be flammable. The agent can die from flames. Yes. All right. And let's do 2 more guesses. I think you can try. I don't know. I don't think so. Any other guess? You want to guess? There are monsters. Yes. What kind of monster you think is gonna kill the player? Like, guess a random monster. Okay. Sure. Okay. Close enough. Close enough. Okay. So you can see that they are chopping trees right now to get some logs. Yeah, and then like right here. Okay. So it's like this is the dusk time right now. And I think I will show you the night. Oh wait, this is morning again. It did survive for 50 minutes, which is day 7. It survived to day 7. It's just like the guy that we follow only go up to day 7, so we just like trying to make rules that based on that guy to give new players. So you can see that during the night it's like empty dark, so it can build campfire to survive the night and everything like that. And it cook berries too. You can see that they cook some food also. Yeah. So let's see how it die real quick. I think the monster, yeah, the monster chased him for like 1 whole day, I believe. Yes. So like if it chases you, so like how we got it, so if it chases you, just run away. We don't try and like, attack it right now. So if it chases you, just run away for now. Yeah. You can trap them or you can beat them with a sword. They are friendly monster too, but so it survived to day 7, I believe.
Sorry if I missed this.
Yeah.
Is there like tick? Like how often does the logic run?
It ran every time there. So like, I think it run like almost every time there is an action. So like it can be actions, it run immediately right away. It's only one loop. There you go. You can see there's a tree monster that's chasing the thing, and so you can see that it's night, right? And the agent know that you cannot survive in the dark, so it used a torch to escape the monster. And yeah, we didn't expect a tree monster. Oh wait, it did survive to that day. Oh yeah, there you go. It just chase you. Yeah. There you go. It finally died from the tree monster. Yeah, and could just continue with our presentation. Just a few more. Yeah, click on it. Oh, wait, what? Okay. So yeah, so this is some statistic. We did 8 runs. The first run is due to darkness. I think it just wander around the savannah, and there's nothing in savannah like trees or bush to make campfire or torches, so it just died in darkness there. And they did die from like out sanity too, which is terrific. I think someone said earlier, but it died a lot to hostile mob and starve hungry. So it did starve, sadly. Yeah. So here's the conclusion.
Right. So in conclusion, our agent was capable of using common sense reasoning to somewhat mimic the wiki guide for a beginner player. So, so yeah, it was able to survive roughly 7 days, given that it was able to outrun several hostile mobs. And so yeah, we were able to model this reasoning with SCAS predicates and survival strategies, and make context-aware survival decisions. So running away when necessary, making food, eating food, staying alive, from fairly understood surroundings, I guess. And so some challenges we faced were specifics on threat distances, right? So once the entity left the screen, so when the player ran away from the tree and got far enough away, it would forget about the tree monster. So, and the tree monster will catch up, and then, so there are quite a few other things. So optimal resource collection, right? So in a savanna, we run out of resources, and intuitive human strategies, right? We can definitely model a better reasoning strategies there. And so future work would be to make better planning, better resource management, and resources, tools and building structures, and incorporate some sort of better memory mechanism to remember things like further away, where you are, and other resources. So.
Also, the thing about this game is also wiki intensive. So like you have to read the wiki to understand how to play it properly. So yeah. Yeah. So thank you. My name is Dan Nguyen again.
Yes, I'm Bryant Hargreaves.
So the issue with object permanence and forgetting about the monster, does the agent keep any kind of memory of like where important resources were, or like are there laws of inertia in the program, or is it just what's on the screen is what it knows about?
It's like outside, out of mind. So yeah. It did remember the previous action though. So like it's like so like how we compute the action is that as soon as we done computing, we compute again and again. So we ignore we don't wait for until the action is done. So it have to remember the previous action, and if we still doing it, then we ask them to continue doing it. Yeah. So that's the only memory we have. But like if it's outside, it's out of mind. So.
Hi, thanks for the presentation. It's very great. I was wondering how it prioritizes between like different needs. Say if like it's hungry and it's like also low health. Like how does it prioritize between these two, or like sanity wise?
So right now it doesn't prioritize. So like we prioritize it in the code wise. So like we can reorder the rules. So like how we compute all the rules at once. So if we put the rules earlier, the earliest rule will get output first, and then it's gonna go down and down and down. So we just take the previous rule. But like we also have memory, so we compute everything to ensure that the previous action is we still doing it the previous action. So we need to continue doing it, because like chopping trees require like times. You cannot just like chop once and it's gonna get you logs. But yeah. Any other question?
It is just a kind of a technical question regarding the whole environment. How is the information about the world provide? Did you have to implement that, or is the game providing some mod interface that has this JSON output that facilitates all of the interaction?
The game is very developer friendly, so it has a lot of scripts and stuff made available for modifications, mods. So a lot of the things that we find are purely available from the base Lua code. So the Lua world, we can get entities from everything. The hard part was parsing those and getting all of those into a format that we could move over to Python and then SCASP. So, which we did by parsing into JSON. So just to make it easier and more readable. Thank you.
Thank you so much.
generate them, but they cannot provide them. So that's definitely a limitation. We would want
Hello, everyone. Welcome to the 7th session of PADL. And we are going to start with Dr. Fang Li, ASP for provenance graph-based cyber threat detection.
Hi, everyone. So actually, the name, this is a truncated name. So because the name is so long, so I just make it shorter, put it here. So basically, the idea of this research is it's a concept proof, a proof of concept that we are able to apply the ASP to the graph-based some reasoning, especially, for example, in this case for cybersecurity threat detection. So let me tell a little bit about the background of this research. So, so the thing is, we got the motivation, says why is this research, but the actual motivation, one layer above this motivation was during my teaching. So I was teaching intelligent system class, and during the class I was trying to promote declarative programming, right? So, and also the department wanted me to teach another course, which is guiding graduate student to do some research, right? Which we're a teaching school, which is very rare. But I was trying to show my student how to write a research paper, start from scratch. Then I started showing them, hey, you need to figure out a topic and try to do the literature research to see is there any similar stuff, and then keep doing, come up with your idea, and then do implementation, write the paper. So before the semester ends, before they even submit their homework, I finished my paper. So, then I know the PADL is the one, it's like in November or something, it's like it's perfect time I submitted the paper. So this is the original motivation. So then the actual motivation here academically is that I was also told that because we have a lot of colleagues working on cybersecurity, so there are a lot of things you need to do. They're very, very hard to find those patterns and to detect the threats or something. It rely on human expertise, some experienced stuff. I said, okay, my professor, my advisor, Dr. Gupta, told me that this is the perfect place to apply ASP, right? So I was thinking maybe we are able to do ASP to handle some of those cybersecurity problems, right? So then I contact the second author, which is another professor at another university. He's working on cybersecurity. I talked to him, hey, is there any scenario in cybersecurity could be represented into a directed graph, right? He was thinking, hey, so he said there's a thing called provenance graph. So that thing is able to, provenance graph is what they use to sort of replace the system log, right? So I'm not a professional on cybersecurity, but he told me about this. So they use the graph, the nodes, and the edges to link the entities. For example, you got a user. The user opens a file, right? So the user is a node, file is a node. Then the edge means opens, also with some timestamp or something, right? And then some process visit internet request, right? Then visit somewhere. So you also link those two entities together using some edge, right? And with some properties for the edge, like timestamp or some whatever, the privilege or something linked. So they put the whole thing as a graph. I look at this as it's very familiar to me, right? So you got components, you got a process, files, connections, which are the nodes. You got edge, you got a read, write, fork for execution or something, and also got temporal information and metadata. So it's very easy for us to model, right? So I said, I'm able to find a way, a different way. Maybe nobody ever done this before to help you guys do some reasoning on those provenance graph, right? So before, we did some literature research. So how people deal with the provenance graph. They use some, they search in the graph, they use some Neo4j, like those kind of implementation stuff, the database. They try to do something, right? So they can do like policy compliance, the forensic, computer forensics or something, and attack reconstruction, try to identify to redone the attack, how it happens. And also the limitation is the queries are very complicated. You're searching on a very large graph, huge graph, right? So, and also the reasoning, they cannot do too much about the reasoning as what we call the reasoning, right? As declarative people here. So I think, okay, maybe we can apply the ASP. So, but why ASP? So ASP, the first thing is declarative, right? Declarative means that programming without how, right? You just tell the computer, what do you have? What do you want? That's it. Computer will figure it for you. This is called AI, right? Artificial intelligence. Not like you need to give the computers step by step, like a C++, Python, right? You need to do this. without your instruction, the computer cannot do anything, right? That's not AI as artificial idiot, right? Sometimes I call it, right? So the thing is, we do this declarative as a good pro, and then based on stable model semantics, right? So, and also supports non-monotonic reasoning. This is the most important part, I think, because for cybersecurity, a lot of knowledge, a lot of patterns, the rules you define, sometimes the later rules might conflict with the previous defined rules, right? What can you do with that? With monotonic reasoning, like a parallelism, so you have to explicitly define everything, right? So, for example, bird can fly. You say like if X is bird, then X can fly. But later you meet penguin. That won't work, right? But for ASP, like non-monotonic reasoning, you have default reasoning. Negation as failure. You define the bird. If it's not abnormal, then the bird can fly. So later, no matter what kind of bird, weird bird you meet, you just label that guy as abnormal. That's okay, right? So this thing is a big plus for reasoning in this kind of task. So in case, so I still have to introduce some ASP, right? So this is the basic syntax. So you got the head, the bodies, right? So you got the positive atoms and also some negative ones. This is negation as a failure. So the not, the NOT with some term is not the same as the classic negation not. The classic not, for example, is you say not P. That means you have proof that P is false, right? But with this kind of not, that means you don't have proof that this guy is true. That's the biggest difference, right? So this is the rule. And also, of course, I omitted some part. So we got the constraints, like the headless constraint, right? If you remove this head, this means what? This means these three guys cannot happen together. If they happen together, you got nothing, right? So that means that's a constraint. Also, we have like a P if Q, comma, not P. This is another way to define the constraint, right? So this is ASP. And why we need to combine those? How can we combine those together? So since we already got the provenance graph, right, which is pretty much like causal relationship, you got this node pointing to this node. We are able to model them use ASP, right? So the targeting node is the head, right? So the starting node is the body. That's it. And then also we can define the whole thing, right? So encode the whole provenance graph into the ASP format. So for example, we got the basic representation. We got nodes, we got a process, right? You got files, you got network, etc. You can have more. Because, by the way, I need to mention that in the cybersecurity community, there's no universal defined provenance graph format yet. So that means it's also a big plus for us. We are open to customize, right? So in this case, the edges, you get from node to another node, the type, right? For example, you accept the process access the file. So the type is going to be access, right? Then T is the time step. So this is the basic, one of the basic one. And here are some core ASP rules. Like one of the ones is reachability, right? So the reachable, this rules define the reachable. So from this node and that node, I mean, can you reach this node from that node through in the graph, right? This is reachability. Then temporal ordering, you need to define which one is earlier, which one is later, because temporal, right? So for the system. Then causal dependency. So it defines these two are, this one is depending on some other nodes. Like we also need to define this kind of stuff. So this is the basic stuff. And also we have some advanced rules for like attack path tracing. So how you got a process, right? You got reachable, then you know this one caused some attack, then you can trace back to find, hey, which guy started this one, right? Or which processes is possibly be affected by this attack, right? So we are able to trace back. And data filtration, that means you want to you define the connection, the process, and the file. So the process did something to the file and send some data somewhere else. So this might cause problem, right? So again, I'm not an expert on cybersecurity. Those are my co-author. We discussed with each other. He give us a lot of this kind of information, right? Again, this paper is a proof of concept. So we just want to bring the possibility. This is the way we can apply, right? So this, this might not be 100% true, right? So, but this is just an example. And also we got the root cause analysis. You want to dig back to see what is the actual cause, the original one, the troublemaker, right? And also for the alert generation, so this is just like some information, a message passing or something. It tell you, for example, unauthorized access to a sensitive file, right? If you got a file is sensitive, somebody visiting this might be a threat, might be not, right? We don't know, but we need to let the user be aware of this, right? So this is one of the things. Now, the capability, so we are able to comprehensive attack path analysis do this, and we are able to detect data exfiltration attempts, and root cause and automated alert generation. Those are based on those rules that we defined before. So the benefits is it's flexible and extensible, right? What is extensible? Because our non-monotonic nature, right? Non-monotonic nature. So, and every user is able to define their own threat pattern, right? Anomaly pattern. So clear expression of security patterns. So with the structure, right? Like ASP rule is pretty much easier for us to understand, right? So, and also integration of temporal reasoning, we got a time step, right? And also support for complex attack scenarios. So it depends on how well you design your pattern, right? The pattern, right? The rules. So like this is example, like a little bit more complicated than advanced rules here. This is a multi-stage attack detection. So based on the compromise, based on the data exfiltration, and based on some of the privilege escalation, we say if anything meets this requirement, it's probably going to be a multi-stage attack, right? So we're able to apply this to help the security people to be alert, right? Like this. And also the detection rules, we're able to detect the privilege escalation by using, if you got a process, previous it has low privilege, and later this guy raised to higher privilege. So this escalation, you need to be aware of this kind of a scenario also, right? So, and the thing is, the implementation part, we use SCASP system, because SCASP is a goal-driven, right? It's goal-driven. So because like a prevalence graph could be very big, very large. So if you, sometimes we just wanted to, for example, the security engineer, they are not sure about some small portion, he can just make a query on that related nodes, right? So you got a pretty decent result of this part. So we try to use Klingo, but it's way slower than SCASP. So we use SCASP. So the challenges, again, I mean, through my entire academic life, scalability is always the nightmare. So this one also being, driven by scalability, right? If you got a very large graph, very complicated scenario, right? Entanglement, right? So it's hard to handle. So far, and the state space explosion at the same time, and the real-time analysis is a problem right now. So far, but just like the survival game, right? You are sort of can do some real time, but it's in the current stage we haven't do anything with that yet. Knowledge engineering, right? This is a very hard knowledge engineering. We need to who defines those rules, right? Who defines those patterns? That's the problem, right? So we need some input. But again, this just want to bring a method to above the table to let everybody see, hey, we're able to do this, right? Our future goal is, I have a little bit ambitious goal in the future. So I want to build a platform, not just like a application, a platform, and also with a DSL, a domain-specific language, provided for the cybersecurity people, so that everybody is able to upload their own pattern, threat pattern, anomaly pattern, whatever, right? So the user able to download those right? Like add-on or whatever thing. So whenever, if you got some, your dot, you got some system log, so you don't know whether your system log, somebody intruded your system, you can upload that log file to the online system, and then you choose the possible attack or something, then you do a scanning, right? So this is going to be my future goal. But currently, we still have a lot of work to do. This is just like a starting point for this research. Thank you so much. Yeah.
So I'm assuming that the detection rules, you wrote them together with a cybersecurity expert. How long did it take to come up with those rules? Uh-huh. Uh-huh.
But to me, those are not so applicable. I simplified those. So like the file exfiltration, like those multi-stage. So it's supposed to be very long. But I don't think it's a good idea to start with those. I said, okay, can you minimize, just like Elon Musk asking his engineers, can you minimize, simplify those things? So the guy just gave me, okay, those you cannot be less than those rules. That's it. That's the bottom line. So I said, okay, I will put the bottom line as our case. So this, some of those rules are come from this way. Yeah.
I have one more question.
Yeah.
The last slide you mentioned machine learning integration.
Yep.
What are your ideas with that for the future?
That's a good question. So because we rely on knowledge engineering, we want to define those patterns stuff. So my plan is to use large language model or something, and then to generate, help us to generate the patterns, the abnormality or threat, those kind of the rules. And also not directly do that. We want to generate some synthetic scenario and try to analyze those. And then, so here I mean using machine learning is pretty much this way, not on the reasoning, just on the defining. Right? Yeah. Thank you.
I think it's not the first time that I make this comment, but don't you think that probabilities could have the expressive power of this formalism? I mean, in order to formalize the model or the problem that you have. Well, I started using logic rules with probabilities at some time ago, and now I think that they are always needed, in the sense that it's almost impossible that you have a domain where the rules are always deterministic, are always clear. Typically, there is some probability involved. So I wonder if this is the case here, whether can you could improve the model using probabilities too.
Before I answer this question, let me just talk about my current change in my belief of research. So I've been with Dr. Gupta all the time, right? So for my PhD, so we are a believer of explainable AI. I believe most people here believe this. But these years during teaching, I started to realize that probability, non-deterministic uncertainty is more important, because we define artificial intelligence. We are not even able to formally define what intelligence is. How could it be possible for us to make an artificial version of it, right? So we need to admit we are limited. So we need to admit some of the system. We're able to build a system which we couldn't fully understand, right? So this being proved to be true, right? Look at this wave of AI, right? So like the chat robot, well, Dr. Gupta was leading us as a team. So Sopam might know that we participated in Amazon's Alexa competition before I graduated, 2021, I believe. We were the 9th team over the 500 teams worldwide. And we were the only team didn't use machine learning. We use rule-based. And so the competition is you build a chat robot. They got a lot of people to chat with the chat robot and to see who lasts longer. which team lasts longer, right? So, but nowadays nobody wants to hold this kind of computation because it's ridiculous. Right now, ChatGPT, every those kind of large language model can chat with people for a long time, right? So why it succeed, and also the application of the hidden Markov model on the speech recognition or whatever things, right? So they applied probability, they accept uncertainty, they admit that we human cannot fully understand this world. So how about we accept the explainability, right? Here is very good question, sir. So for our system, the same thing. Eventually, I want import probability into all of my research. All of my research, more or less, maybe different level, but I need to handle the probabilities. For here, you see, I noticed there's some ASP approach has non-deterministic, right? Has a probability integrated temptation right now. So next stage, I also will look at those kind of papers to see whether we're able to do some integrate the probabilistic reasoning into our platform. So the other thing is, for now, I was told that like in cybersecurity, there's no like a universal, like a formalized definition of those attacking or something. So so that's why we're open to customize. So everybody is able to submit their pattern or something, right? So because we're not monotonic, so this should be okay. The whole platform should be able to handle the thing, right? Thank you. Yeah.
And our next talk will be recorded. It's titled Leveraging LLM Reasoning with Dual Horn Programs by POPL'25.
Hello, my talk will be about leveraging LLM reasoning with dual horn programs. A few words about why this is interesting. Well, let's start with the fact that negation as failure cannot provide bindings. It can filter existing bindings provided by other goals that generate them, but they cannot provide them. So that's definitely a limitation. We would want something that can positively state reasons why something is not provable, which negation as failure cannot do. So for that reason, we will revisit dual horn clause programs that deal constructively with negative information. This is motivated by the fact that there is an abundance of positive or negative facts that could be generated when LLMs are convinced to explore recursively a given fact that we would like to see what consequences it has, and that would lead us to dual horn logic programs. We want to ensure that reasoning is constructive, and this will happen with the combined horn close and dual horn programs. And there are, of course, applications, in particular applications that take advantage of LLM-generated logic programs, providing a very interesting combination of backward reasoning, goal-oriented backward reasoning, and also goal-oriented forward reasoning. So let's start with this strong statement that negation as failure is considered harmful, a rephrase of Dijkstra's statement about go-tos at the time. Well, there is an interesting anecdotic mismatch here. The cat has been systematically vilified as procedural, non-declarative, and at the same time, negation as failure, which is in fact a two-liner expressed in terms of cat, has been glorified and also fine-tuned and refined in various ways in hundreds of very nice otherwise papers, and had an impact on developing new fields, in fact, in particular answer set programming. Now, beyond the anecdotic, let's look at the facts. Negation as failure tacitly elevates failure of a meta-level proof procedure into a construct of the object language. Negation as failure cannot explain, as no bindings of variables are provided. And while it is a shortcut that's very useful in programming, like not member of a given finite set would be an example, it conflates key concepts of truth and probability. And that's not a good thing for knowledge representation. So let's make a few steps toward constructive logic programming now. Well, horn clause resolution with clause expressed in implicational form is intuitionistic valid. It's not the typical presentation of resolution, but it can be very easily morphed into an implicational form where inferences, instead of having positives and negatives cancelling, would just propagate along implication lines. So negation as failure relies on a fallacy that true P implies provable P. This is the questionable part. Otherwise, by modus tollens, we have that not provable P means not true P, and the combination of those actually gives us something that we know since Gödel, that there are unprovable true statements in an interesting language or theory. So intuitionistically, falsehood needs to be proven constructively by deriving an actual contradiction and without reliance on P or not P as an axiom, as it happens in classical logic. So this leads to our challenges expressed here as two open questions. Can we do logic programming while staying in a constructive, intuitionistically sound framework? And then, can we benefit from the knowledge encapsulated in the LLM's parametric memory while staying in this framework? So let's look at our answer to these challenges. Dual horn clauses. They have been discovered a long time ago as part of Schaeffer's dichotomy between P-complete and NP-complete subsets of propositional logic, among other things. But let's compare them directly with definite horn clauses here. So the disjunction-based notation tells that there is a positive one, that's the head of the clause, and several negative ones. Implicationally, that means, as we know from prologue, the head is implied by the conjunction of the literals in the body. Definite dual horn clauses will now, in disjunction form, will have one negative clause head and several disjunctively related positive ones, which also means, if we rewrite it implicationally, that the head here implies a disjunction of the literals in the body. So we look at the implication arrows here and here, and we look at the conjunction here, dualized as disjunction there. Of course, we have also integrity constraints, and integrity constraints, the most well-known ones tell that those propositions cannot be true at the same time. They would imply false. And that's the disjunctive form. And then for dual horn, it means that this disjunction here must be true, therefore at least one of them needs to be true. While here, we say that they cannot be all true here. In particular, when there are two of them, that's a form of weak negation, saying that P1 and P2, well, contradict each other and would imply false if we put them together, without bringing in that one of them needs to be necessarily true, as it happens in classical logic. So these are the interesting relations between those implicational and disjunctive expressed forms. The implicationals are weaker in intuitionistic logic, but they are equivalent in classical logic, so they collapse in classical logic. However, we prefer the semantic of the implication as we have it in horn clause logic, and that means that actually in intuitionistic logic we are dealing with a weaker inferential system, which is a good thing. The fewer things you assume and the more you can prove out of them, the better it is. Dual horn clauses then bring us to falsification as the key objective that we want, but done constructively. So dual horn clause is a disjunction of literals with at most one negative literal, or exactly one if it's a definite one. Same thing for dual horn clause programs, being a conjunction of dual horn clauses. We have a prologue-like syntax here, and we represent implication arrow with prologue syntax with this double arrow here, and we represent disjunction as the Prolog way of doing it. A negated fact would become S implies false, corresponding to true implies S, or S if true, as we know from definite Horn-Close programs in Prolog. So this is a small example of a dual Horn-Close program. Implications, P implies Q or R, and so on. Now, what we can do is this in a goal-oriented fashion is that we can falsify it by backpropagating falsehood from its consequences. So let's do it for P here. So for P, if P happens to be true, then Q or R is true. It means one of them needs to be true. Well, let's follow that Q would be true. For Q to be true, one of R or S needs to be true. Now, we know for sure that R is false. This makes this deleted here. So we still have S being possibly true, but S we know is false. Therefore, Q cannot be true. We get back here, it cannot be true. And R, we have seen that it cannot be true. Therefore, P cannot be true. We falsified P because its consequences brought us to falsehood. And that's how falsity backpropagates, very much like truth backpropagates from facts when we hit them in SLD resolution working on a Prolog. So let's look at a typical use case. So the objective as dual Horn programs is to describe constructively why something is not true. Therefore, we want to falsify the initiator goal by backpropagating, as we have seen, from its negative, in a more general sense, undesirable, unwanted, harmful, impossible, and so on, consequences. So we see here an instance of goal-directed forward reasoning. What we have as a nice property is a polynomial complexity for the propositional case that's found in Scheffer's dichotomy theorem. So it's a P-complete class, very much like Horn-Clauses. And the nice thing about that is that because LLM generated programs that could be very large, LLMs know a lot about the world, will be propositional. Therefore, we don't have a problem computing a fixed point with a fixed points computation, that minimal model in basically linear time. This brings us to our embedded language into Prolog. Symmetric logic programming, SIMLP. It combines Horn-Clauses and dual Horn-Clauses into Prolog. Now we have a bit of syntax here. We mark with plus facts that are true and with minus that are false. That's a shorthand. And then we use this to represent implication, and this to represent reverse implication. So minus P is a shortcut to P implies false, and plus P is a shortcut to true implies P. So we borrow from Prolog the usual notation for conjunction and disjunction, and that's the syntax. Now we have a compilation scheme. Let's look at this clause here in dual Horn form. So P0 implies a disjunction. Well, we have kind of seen that we solve it by falsifying its consequences. So the idea is that if we turn it into a Horn clause by saying we turn this into P0 if P1 and Pn, so the dual actually, And we place the result of all those compiled forms into a module false, then we know that if they succeed in the module false and they produce bindings, if we have variables, which we could, then they would express what cannot be true constructively. So a successful proof in this module false then implements successful falsification of the original dual horn clause. And this compilation ensures that backward reasoning on horn clauses mirrors forward reasoning on dual horn clauses, and it preserves efficiency and logical correctness. So now let's look at a first example. Well, this could be politically relevant in the upcoming month in US. Losing the Fed's independence. What would be the consequences of that? And we'll explore that at multiple levels of recursion. So at first level, one of the things that come out here is increased political influence on monetary policy, with consequences, among them not very good ones: short-term economic manipulation, eroded investor confidence, heightened market volatility, policy-driven inflation risks, and then we can explore eroded investor confidence further down and some of the negative consequences, exploration level by level. So if all those things turn out not to be a good idea, we could hopefully convince a decision maker the Fed's independence is not a good idea. So the machine that handles this recursive unfolding to extract from the LLM's gigantic parametric memory very specific knowledge centered on a given topic or statement is this deep LLM application. It's available as a Streamlit app, and in the paper there are multiple links to code. So it works by on the positive Horn subset by doing SLD resolutions, close selections via unification, but this is actually replaced by an LLM-driven dynamic close head creation with an option of focusing by proximity of embeddings to ground truth facts. So it's a multi-agent system actually, kind of ahead of today's emphasis on agentic systems. It's about a year and a half old. The DeepL element has been described in more detail in several previous papers that are cited in the paper. Now we have a client-side management of the LLM's memory, and we work with the equivalent of a gold stack and a gold trace, recording our steps on the current search path. Instead of variable bindings, when we work in the propositional domain, answers would be traces of justification steps, clearly explaining where they are derived from. And then, when depth limit is reached, the items on the gold stack can be treated as abducible statements that can be hypothetically assumed and then checked against integrity constraints. In particular, they can be checked by seeing their consequences in a dual Horn program. If the consequences lead to unpleasant facts, negative facts, then we will interpret them as failing. Otherwise, we will interpret them as positive abducibles. They could still be filtered out by integrity constraints once assumed. So exploring a topic with deep LLM, well, we have choice of topics here, in particular for dual horn programs. We are interested in consequence predictions. And here we choose abducible clauses in the open world semantics for horn clause programs. That's a relatively complex and focused and narrow concept in a way. And we can see here how it reduces to several more refined concepts that we could then describe as a logic program as we see it here with disjunctions and conjunctions in it. So that's basically what DeepLLM does for us. And now let's look at some applications of programs that could be either handmade, like I did this one, or generated by an LLM. So this is default reasoning dual view. Usually to compile and execute, we include compile clauses.pro. The compiler work as a term expansion mechanism, so it's very little bureaucracy with it, like compiling to a file, then loading it. That's not happening. It's just expanding the dual horn clauses into corresponding horn clauses in the module false. So a bird can fly, and for that it should not be a challenge bird, which means that if we have that eagle joy is not a challenge bird and humming jenny is not a challenge bird, then they would fly. In fact, we don't even need to say bird here. It's enough to say that they're not challenge bird in the module false, and then we accept that they fly. That's kind of more direct than the corresponding famous default negation-based interpretation of the same Tweety problem. Let's look at something a little bit more interesting, how we combine positive and negative advice in a SimLP program. So this is about a little stock market advice, about a cautious, kind of conservative-ish buy. Something needs to be recommended and also safe. So things that are safe are if they are in the false module volatile, so if they're not volatile, if they're not overvalued, and if it's true that they are stable. So you see the module true where the horn clauses go, and the module false where the dual horn clauses go. So we have a series of facts here about some of the stocks. I didn't use the tickers, I just expanded them so people might recognize what they are. And we have here what volatile means as an implication, big price changes in the last month, and then we see who didn't have big changes in the last month and who's not overvalued. And based on that, we can now run it, and we see in the module true we call cautious buy, and we get the answers for QQ, Apple, Meta, and Berkshire, which are a subset of the things that got recommended here. So after combining positive and negative facts and inferences drawn in the horn module true and the dual horn module false, the call to cautious buy in module true will generate the answers that I just showed. So what are the merits of this? Well, integration of positive and negative advice for practical reasoning, evaluating stocks for cautious investment in this case, rules combine negative warnings like volatility and positive assurances like stability. It facilitates a nuanced and data-driven decision-making process, and of course it shows the utilities of horn clause logic in a real-world context. So let's look now at some of the other deep LLM generated horn and dual horn programs. They generate propositional logic programs. We have goal-driven backward reasoning in horn clauses that decomposes complex tasks into disjunctions and conjunctions of simpler tasks. And then we have forward reasoning that dually help explore consequences of hypotheses with the purpose of being eventually falsified. So the deep LLM system recursively explores a topic of a given depth, and it's, as I said, an agentic system with interactors to manage the LLM interaction task, recursors to handle iterative subtasks, and then the refiners that enhance clarity and verify reasoning steps. In particular, they could veto some of the conclusions here. So they are basically critical agents that filter the enthusiasm of the recursors otherwise. Logic program generated are explainable and modular, and then as a practical consequence is that deep LLM can minimize inaccuracies and biases in LLM outputs. So here's another one related to escalation risks after use of tactical nuclear weapons, and that could lead to a global nuclear war or uncontrollable retaliation steps. This is explored deeply with a lot of consequences, and then hopefully again a decision maker would refrain from proceeding with something like that, knowing how bad the consequences are. So now let me finalize before we get to the end. Dual horn programs versus constructive negation. So while dual horn programs produce bindings of the form x equal t, with t a term, a ground term usually, constructive negation reduce negated goal to bindings of the form x different from t. So they tell what x cannot be, information only useful if a generator provides candidates for what x could be, and they are usually part of a constraint solver where that's happening, and then they help, of course, making the constraint solver more efficient. But what we discovered or recovered here is a genuinely constructive mechanism to deal with inference about negative facts without tacitly reflecting the failure of the proof procedure at object language level, as in the case of negation as failure and its constructive elaborations. So the conclusion would be that we bring in dual horn clauses that have syntactic simplicity, have a straightforward semantics. We have a compilation scheme for them, and in CMLP, this embedded language, horn and dual horn programs combine fully constructive, intuitionistically valid reasoning about the two sides of a decision process. Using the deep LLM system, we can generate goal-oriented backward and forward reasoning propositional programs, and for very large LLMs generated programs, we have actually a linear algorithm to find the unique minimal model, because we stay in the P-complete realm. So we believe that our effort has revealed a novel form of synergy between generative AI systems and the logic programming tools. Thank you.
Because Paul Tarao is not receiving our questions, but we are not receiving the feedback. I mean, we're not sharing the feedback. So it would make sense that we make the questions, but at least each other
For instance, I have a question. So who knows? I have a comment. Yes, I have a comment. I mean, there's a little cheating about this because he's considering just constructive negation, but there are many flavors, as we saw in the keynote presentation. For instance, there are compiled time versions of constructive negation, like intentional negation or constructive intentional negation. So in those cases, I mean, in general, you cannot change a negative answer, a negative binding by a positive binding, because there is no finite representation of negative information. The equivalent of a closed negative formula using disequality constraints in general is an infinite conjunction of equality constraints. And this is something that is not mentioned in the conclusion, right? And that is one of the problems, that this is not so easy. It works for propositional dual Horn crosses, but it doesn't work for some of the recursive Herban universes that are mentioned in the long paper. So, to put it shortly, if we consider dual Horn crosses as the other side of the mirror, the dual to conjunction is the injunction, the dual of positive is negative, and the dual of existential variables are universally quantified variables. So in general, if you have existentially quantified variables in standard Horn crosses, you should have universally quantified, but universal quantification in general is problematic. So that's overseen in the conclusions, and I think that the comment should be made.
In that case, let's move on to the next talk, Enhancing Network Diagnosis with Reflection in Prologue by Anduo Wang.
Hi, Anduo Wang here with Temple. In this presentation, I will talk about enhancing network diagnosis with reflection in Prologue. So why network diagnosis? On the surface, networking has been a tremendous success. Just look at this internet today, this global infrastructure. Compare it with the original ARPANET. But if we look closer, inside, network management is a completely different story. Network systems are increasingly complicated. The traditional network diagnostic tools based on trial and error, pin and trace route, became a black art that's no longer adequate. So in the past 10 years, to address this limitation, we are seeing more and more use of static analysis for diagnosis of networks. And here's a few publications appearing in major networking venues. And here's more events in both industry and academia. So one notable thing we observe here is the majority of these work are on verifying data centers. These are lightning-fast network verification tools for hyperscale data centers developed by big companies like Microsoft and Google, etc. A key enabler here is the use of software-defined networking, SDN, that views a network as a network-wide program. This program perspective transforms network diagnosis into a static analysis task. What is often neglected in this data center diagnosis, I would argue, is a unique characteristic of data centers. Data centers, unlike any other networks, they are clean slate, homogeneous, well-planned, and over-provisioned. They play a key role. This becomes even more clear if we make a parallel between formal diagnosis in data center and program analysis in compilation. In both compilation and data centers, we are facing problems that are well understood and oftentimes prefixed, where the performance is the major concern. For example, compilation, we deal with optimization. And in data center, almost all the tools we've seen in the previous slide, they're about reachability verification. So not surprisingly, despite their difference, both solutions oftentimes take the form of highly optimized heuristics over carefully crafted data structures. But in the wild, the majority of the networks, they are not like data centers. They are not a clean slate. In the wild, no two networks are the same. And networks are always evolving with unanticipated changes. Just like in the generic programming environment, no two programmers are the same, and we need to support the entire life cycle of software development. In other words, the problems in programming environment and in the majority of networks we need to deal with in the wild, we are facing problems that are more diverse compared to data centers. We need to support the entire life cycle of the system. And here, in addition to performance, usability also matters. We need simple, flexible, and extensible support. And we argue that the solutions that originally developed in general programming environment, such as profiling, monitoring, tracing, or the more sophisticated algorithmic debugging, abstract interpretation, program slicing, etc., these tools, they will have great potential for networking as well. And in this talk, I want to present some initial encouraging results in developing explanation and test generation tool for networking by using Prolog. The idea here is that Prolog provides a very natural way to write meta interpreters that offer an injection point of these new solutions. In particular, I want to show you how Prolog can help us debug internet routing, how Prolog's unique programming style that combines declarative logic and imperative control offers a natural spec for the dynamic and non-convergent behavior of complicated internet routing behavior, and how Prolog's meta-programming facility allows us to quickly write meta-interpreters that can explain the internet routing behavior. But first, let me provide some necessary background on internet routing. Internet routing is about computing paths between any pair of source and destination on the global internet, oftentimes across multiple independent operated networks, the so-called autonomous systems or ASs. To automatically do this job, internet routing uses BGP, Border Gateway Protocol, as a distributed algorithm. So BGP computes, in networking jargon, inter-AS paths, a shortest path that modulated modular traffic policies set by individual ASs along the way. Traffic policies are necessary for ASs to express their local, oftentimes economic concerns. Just like most things happening in computer networks, BGP is not a protocol that's well planned. It's incremental patchwork. It involves a sequence of attributes that are orderly compared in path selection. It also involves several scaling methods. What's relevant in our talk here are two attributes and one scaling method. The first attribute is next hop that allows us to select the closest exit point. The idea is every AS, consider the center AS example, every AS would like to get rid of traffic as soon as possible. So we always pick the shortest internal path, in this case highlighted by red path. The next attribute relevant to our debugging here is MAD, multi-exit discriminator. MAD is the attribute set by an AS to express its preference how traffic enter it. For example, ASX can use 10 and 100 to be associated with CA and CB link here, expressing that it favors CA over CB to receive traffic. And finally, we need to understand reflection. Without reflection, BGP requires full match between any pair of BGP routers so they have consistent view. But with reflection, the idea is some routers now will serve as reflectors that reflects routes on behalf of other nodes. Clearly, reflection is a very useful scaling technique to remove that full match requirement. So at this stage, we've discussed 3 important aspects of BGP. Each looks very useful, but putting them together, we will see unexpected, indeed harmful result, oscillation, as highlighted in this example, first introduced in RFC 3345. In this example here, we are interested in computing paths to the destination in the bottom. The interesting part here is AS1. AS1 has 2 reflectors, RA and RD, that are connected with each other, and they will reflect information on behalf of each other, as well as RB, RC, RE. So initially, RA and RD each gather information from their direct neighbors RB, RC, and RE. RA will have 2 options, as we can see on the RA column here. Out of the 2 options, RA will pick the red path because it has a shorter next hop cost. On the other hand, RD will simply pick the blue path. That's its only option. Now in the next iteration, RA and RD, they will reflect their information to each other. After RD receives information from RA, which is a path, RD now have 2 options, and out of the 2 options, RD will stick with its old blue choice because it has a better MED. On the other hand, after RA receives this new blue path from RD, RA will change its selection. What's interesting here is the newly arrived blue path will beat the previous selected RA-RC path. However, it wouldn't make the blue path itself the best path for RA. Instead, it will cause RA to reselect a previously discarded red path. Next, as RA and RD each has updated their routing path, they will reflect and notify each other. So in the next iteration, after RD receives this new path from RA, it will update its current best path accordingly, and that will actually trigger RD to change its selection, as highlighted in the figure here. Similarly, after receiving the update from RD, RA will change its selection again. And now we can see a repeating pattern. RA is going back to its oldest state, and similarly, RD is going back to its previous state. And such oscillation can keep forever. So through this simple example, we see that seemingly innocent BGP configuration can lead to undesirable oscillation behavior. What is worse? It's tedious to detect manually, and to our best knowledge, despite of the significant progress in data center verification, none of the existing tools we are aware of can debug, can explain such oscillation. And in the rest of the talk, I want to show you how Prolog can help us to debug it automatically. Our Prolog implementation was tested in XSB and freely available on the GitHub repository here. But in this table, I want to show you how compact and concise our code is. You can see that the BGP protocol, of course, we didn't implement the complete protocol. We only implement the aspects relevant to our analysis here, the IBGP, so-called internal BGP part here, which is 77 lines code. But still, it shows you how concise it is to program in Prolog for BGP systems. And more importantly, the meta interpreter, which is responsible of generating the explanation, is only 10 lines of code. In the repository, you will also find test generation code, which we used for the data plane explanation, which didn't appear here in the talk due to limited time, but we did briefly discuss in the extended abstract. We also have some utility code, such as pretty printing for the explanation. And in the next few slides, let me give you a little bit more feeling of how the Prolog code looks like. First, let me show you fragments of our BGP Prolog encoding. At the top level, to run the BGP system, we first initialize the network, initialize S, and then evoke the net procedure, which run BGP in n steps. We explicitly run it in n steps because we don't know whether the BGP system will converge or not. And in each iteration, the net procedure will call a delta function that transforms the network state from S to its next state M. A network state is really just a list of 3 elements: routing tables, message queues, and pending nodes. And in each transformation of delta, we first pick a node, random pick a node out of the pending nodes for BGP process, which is the BGP process procedure. In the pick procedure, we make use of the member function. And that's the important part because member function is what actually introduces non-determinism into our BGP code. In the BGP process procedure, as we can see here again, the Prolog imperative reading helps a lot. We see that BGP process is really just sequentially evoking these procedures. Compute a new route, locate where it is, inserting a new route into the queue, process a new route with BGP select route, etc. And BGP select route is a part where we actually do path selection, as we've seen earlier in the RFC example. In our simplified version of BGP, we only compare MED attribute and the next hop. So this should give you a high-level feeling of our BGP encoding, and in the GitHub repository, you will see everything. And here is our meta interpreter. And you can see that our meta interpreter is really just a direct extension of the famous 3-line vanilla Prolog meta interpreter. Our meta interpreter is different from the vanilla version in 2 aspects. First, in addition to interpreting a goal, we also generate the corresponding proof of tree. Second, this proof of tree only collects relevant information. We selectively printing what's needed for explaining oscillation. In particular, we are only interested in collecting net. At a high level, each iteration net procedure, and the pick procedure, which node was actually being picked for BGP execution, and finally, the BGP select route procedure. For the rest of the procedures, we just hide them, don't print anything. And this is meta interpreter. Running this meta interpreter on the wrong IBGP procedure we've seen earlier that describes the BGP system, collecting the proof tree, selecting proof tree T, and print it, gives us a trace, gives us a selective trace that actually explains the oscillation behavior. So recall that in the beginning of this talk, I mentioned the significant advancement of network diagnosis from a black art with pen trace route to formal analysis. And our effort here, obviously, is part of that big transition. But among all these efforts, I want to mention a specific tool called Badfish. Because Badfish is also based on logic programming. Badfish is a network configuration tool, uses Daylog as its evaluation engine. Originally introduced into the networking community 10 years ago. Ever since, Badfish has been the backend engine for many analysis tools used in both academia and industry. And in 2023, the Badfish team published an experience paper on the evolution of Badfish with very interesting findings. On one hand, they praise Daylog as a very useful tool to rapidly prototyping new analysis functions. But on the other hand, they also reported the limited expressiveness of Daylog and the lacking of performance, which eventually led them to abandon Daylog and how they moved away from Daylog to Java. In our research, on the other hand, while we agree with Badfish in the use of logic programming as a rapid prototyping tool, we argue that it's too early to abandon logic programming and stop with Daylog. In fact, in this talk, we made the case that Prolog is a very expressive tool for capturing complex, dynamic, non-convergent behavior of computer networks. And more importantly, Prolog can provide metaprogramming facilities that allow us to easily explain the non-convergent behavior of network systems. To conclude, we draw a parallel between formal network diagnosis and program analysis. Our main insight is that the majority of existing network diagnosis in clean slate data center resembles program analysis in compilation, where the problems are oftentimes well understood, prefixed, where the concern is focused on performance. And as a result, solutions there will highly optimize the heuristics over carefully crafted representations. On the other hand, the majority of the networks where formal network diagnosis are needed more resemble programming environment. Here, the problems we are facing are more diverse. We need to support the entire life cycle of the system. And in addition to performance, usability also matters. And our main conjecture is that the tools developed for net programming environment, such as profiling, monitoring, tracing, and more sophisticated tools, including algorithmic debugging, programming, slicing, etc., have great potential in networking as well. And in this talk, we presented some very early stage, but hopefully promising result on using Prolog to implement an explanation generator. Moving forward, we will use Prolog meta interpreter as the injection point to include more new solutions, such as sophisticated algorithmic debugging and program slicing. So that's all my talk. Thank you, and I'm now ready for Q&A.
Just mute. Okay, hi, can you hear us?
Yeah,
Yes.
I can hear you.
Okay. You want to?
I have a question. Towards the beginning of the presentation, you mentioned the problem of oscillation. Is that one of the reasons why it appears? Is it because the policies are not prioritized? There's no ordering of those policies? I'm not very familiar with the domain.
Mhm. Oh yeah, so I can quickly clarify. In the BGP system, in general, there are two sources for oscillation. One is what you mentioned on the global internet, the autonomous system, the so-called independent operating networks, they are not coordinating. There is no universally agreed upon guideline or policy. So the policy themselves can conflict with each other. Yeah, so this is the first type of oscillation. And there is also another source, the kind of oscillation that we were actually trying to catch in this extended abstract, which is due to partial visibility. So in this case, or in the example presented in the top here, you will see that the so-called MED attribute, it was only compared for a particular neighbor AS due to its semantics. So the comparison process, it doesn't compare all the candidate routes, it compare among the subset. But as you can see with reflection now introduced into the system, the reflector will selectively announce, reflect a partial set of points. So the combination of reflection and these MED semantics combined, they will create this very interesting partial visibility into the set of paths that depending on what path you see, you will pick different best paths, and that can lead to oscillation. Actually, it has a close connection with monotonicity.
Thank you. Other questions? Okay, so let's thank the speaker again. And this is the end of the last session. I don't know if the organizers, the chairs, want to say a few words. Yes, no?
So we would like to thank you all for coming here, participating in the symposium, and also the discussions interactively. So we are all happy to see you here, meet you here, and then hopefully we will meet again at the future PADLs. So we don't know yet where PADL will be next year, but maybe we know, huh? POPL? I don't know where POPL will be next year. Do you know? No, we don't know. So we will know it after we learn where POPL will be next year. So that's it. Herman, you want to say something? Yeah. Thank you.